Thank you, and I have to share screen. So my talk is on industry academia efforts to accelerate India's move to net zero. Most of you have heard by now that our Prime Minister announced that by 2070, we will go to net zero. Now, there are two aspects of it. So what we are trying to see that can we speed it up? By 2070, there is going to be a government-driven program, but can we, researchers, industry, and others get together and speed it up? The reason for speeding up is the recognition that while GHG emission is going to hurt the whole world badly, it is going to hurt India much worse because we are in we are much less protected than the rest of the world. Even the mildest climate change is starting to impact us. Most of us who live in Chennai over the last 10 days would have seen that we didn't have very unusual rains, and yet half the city was totally flooded. And there were people who were using boats to come to the office after 2 or 3 days, 4 days. One of the reasons why the focus has not been very strong in India is that India is only 103rd in terms of per capita greenhouse gas emission. And the approach still recently has been, that is not our problem. We are not creating. In terms of the, we are only 103rd in terms of per capita greenhouse gas emission. But we often forget that in total terms, we are already number 3 in the world. And worse is that we have, the good part is that we have very rapid GDP growth. But along with very rapid GDP growth is coming a very rapid GHG emission, which has increased by 335% since 1990. And the way we are going on doing it, we'll probably become number 2 in 7 to 10 years. And therefore, we have to do something. What do you do? India is not a country with a lot of money. And expecting the government will spend billions of dollars, unlikely to happen. We therefore decided at IIT Madras Research Park to take a totally different approach. We said that instead of trying to go after government and trying to push government or demand this or that from government, we said, let's see what the relatively well-to-do people, the upper middle class in India can do. What can industry do? What can commercial buildings like IIT Madras Research Park could do? So what we sort of said, basically, this section, industry, commercial buildings, the upper middle class, the high income group, really have access to money. We can raise money, provided there is a return on investment. So we said, focus on trying to get return on investment for any technology. That will get us to move things much faster, We recognize that 65% of electricity in India is consumed by commercial sector, by industries, and high income group residents. And today they pay between 6.50 rupees to rupees 11 per kilowatt hour. For the €1 is about 84 rupees, so you can actually do the conversion. IIT Madras Research Park, where many of us are right now sitting, itself is a 1.2 million square feet. It's a commercial come industrial complex. It consumes 40 megawatt hour of electricity per day, and we pay close to 9.15 rupees because we are partly commercial, partly industrial. What we are doing is, on the rooftops, we can only get up to about 10% of that, 4 megawatt hour a day. We decided to therefore set up solar and wind plant outside IIT Madras in Tamil Nadu within 200 kilometer radius and wheel energy to such park. We have just signed up on 2 megawatt solar. We are planning to do for 2 megawatt wind, and we'll do more solar and basically get to 80, 90, probably even higher percentage of our total 40 megawatt hour coming from solar and wind. There are policies which allow us to wheeling this energy through the transmission and distribution network that the various companies have, including the state electricity board. We of course have to pay, but they're fairly high, but 2 rupees 50 paise, 3 rupees per kilowatt hour, but still it is doable. Then we will put storage, both the chilled water and battery storage. What is the most interesting thing is that in doing so, if we do it optimally and properly, our cost is under 8 rupees per kilowatt hour. Today we pay 9 rupees 15 paise per kilowatt hour. And by going to 90% solar and wind, putting the right chilled water and battery storage so that whenever electricity is generated, it is either stored or used, we are going to save money. Now, if this works, and we are going to show it over next year or so, in IIT Madras Research Park, why can't it be replicated in almost every commercial complex? There are 40,000 such commercial complexes. And then go to the industry, and then go to the high income group residences. All of them can spend this 8 rupees will further go down over time as the storage cost comes down. So we'll start doing it at 7 rupees per kilowatt hour. Can we get 65% of this electricity away from coal? That's a goal number one. This is what we are trying to do, and we are very confident. The next step that we started doing after we worked out this and said this is something that we pursue, there is some technical work and there is a lot of commercial work in this. At the same time, we started saying these are technologies which are doable in 0 to 5 years. I'm talking about which can get into early commercialization. I'm not talking about those which are only in R&D phase. In 5 years, I can put all these technology which I have put here in the blue as early commercialization. Solar, wind, wheeling of renewable energy, grid storage or chill, water, battery, energy efficiency improvement in AC and heat pumps, strengthening, of course, will require strengthening of transmission and distribution grid for renewables. Hydroelectric storage already there, 2-wheeler and 3-wheelers is already happening, and a good energy management system for vehicles. There are, however, some things which will take longer. They will start now. For example, while the solar is already giving us between 2 rupee to 2 rupee 25 paise per kilowatt hour, we believe that this will further go down as perovskites comes in and wind turbines with larger capacity and high heights actually comes in. So that work also has to start in the 0 to 5 years. Electrification of construction equipment becomes a very, very crucial thing, because today the construction equipment is all run from diesel, highly polluting. Electrification of agricultural equipment which can also start. Of course, they will probably not be done fully in 5 years. Let them spill over to some years. But we actually need many more things where R&D has to start in 0 to 5 years, but commercialization will take 5 to 10 years. One of the first things that we identify is longer term storage. The lithium-ion battery storage or chilled water storage is all right for 1 or 2 days storage. It is not all right for 2 months storage. Whereas zinc here and aluminum, zinc here in particular, you consume zinc. Zinc gets dissolved into electrolyte during discharging, and you can charge it at any other time and regenerate. This is something which certainly will be commercially viable in 5 years. But for making it being commercially viable, we need to do prototype over the next 1 year, and we need to do probably early pilot in 2 to 3 years. Similarly, ocean wave, tidal wave energy work needs to be done. Larger EVs and freight transportation. In 5 years, they will be commercially viable. We need to do work today. Generation of green hydrogen is going to be one of the major things. We need to start doing R&D work and push things. Today it's just too expensive. What can we do to bring down the cost? Every rupee saved there will make a difference. Then use of green hydrogen for cement production and all kinds of things, not just cement production in terms of calcification, but also see how carbon dioxide can be captured from the calcification process and probably pushed into cement. Similarly, use of hydrogen, green hydrogen for steel production. Carbon capture, utilization, sequestration, We have to start examining. R&D needs to be done today so that some commercialization takes place in 5 to 10 years. And some may go beyond this. There are other technologies, for example, small modular nuclear reactors. We are not even sure what all is required, but definitely this can play a very important role, or compressed gas. There may be early R&D has to start. So this is the kind of a program that we started working. IIT Madras and IIT Madras is a department found has competence in all this area. And we said, the first part of any technology exercise is commercialization, R&D. And we'll start the R&D. From R&D, we need to go to the pilot, early pilot. Part of the R&D and pre-commercial pilots has to be funded by either R&D or CSR. But we like to, in the middle of the pilot, we would like to start making commercial sense. That's a time commercial funds actually take over. And the early implementation, which you are doing, by the way, a research park for solar and then full scale implementation. We have understood this process and we are going to drive that, taking technology after technology that I have listed through all these 4 processes. And we have a fairly large team. We have a whole lot of people, Kaushal Jha, Sandhya, Devarajan, Nanda, Sushan, Bharti, already working in batteries, electric vehicles, solar, motors and controllers, battery recycling. But we have professors from IIT, Satya Seshadri, Arvind Chandran, Rajneesh Kumar, who are very good on, for example, zinc air battery, carbon dioxide sequestration, cement, other things. And I think together we have a team, and I've added a few more names, which actually can drive this, and we are doing this. For example, solar, wind power wheeling, 2.5 megawatt-hour chilled water storage, we are doing today. Energy management for green grid, we are doing it today. EV subsystem development, motors, batteries and chargers, and battery swapping, we are doing it today. And I've also put out who are all working. Efficient motors and controllers, Chandran is driving. Enhancing cooling and heating efficiency in commercial industry buildings. We will have different people driving, including Satya Seshadri and the company ZB. Solar system for small and mid-sized complexes. Bharti Balaji and whole lot of people are actually working. Recycling, lithium-ion battery work is going on. There is a new initiative being taken up. How to take the internal combustion engine autos and vehicles like Tata Ace vehicles. These are used for commercial goods transfer. Can we fit our motor, controllers, batteries, and chargers? This morning, after the French delegation actually took them in an e-rickshaw where all these things were fit. Vehicle to grid work is very, very important. It is some distance away, but we need to start working, and we are starting to work. Similarly, retrofitting agricultural diesel machinery and construction machinery, this work will start. More important, zinc air battery. We have a commitment that in 1 year we will get a prototype working 5 kilowatt-hour, driven by Arvind and Satya Seshadri. Chilled water storage, we are already doing it, but we are now going to add hydrates to that, so that in the same size, the capacity becomes 5 times. And besides Kaushal Jha, we will have RK working with us in getting this done. Similarly, we are working on taking a 300 kilowatt-hour chiller here, and we are retrofitting heat pump into that with help of Satya, and trying to not just make both chiller come heat pump from the same unit. Hydrogen generation. Again, we will have that working, and developing a 2-wheeler and 3-wheeler with fuel cell to run on hydrogen. And Arvind will actually drive that. And then we will work on carbon dioxide capture for cement kiln, processing through electrolysis to generate syngas, carbon monoxide, and hydrogen to heat the kiln back. Again, the whole team of professors at IIT, Arvind, Satya, and Rajneesh, all three will actually be driving. and they'll be talking about. We have one more very, very interesting work going on. This is by another group of faculty members at IIT Madras in civil engineering, which are working on decarbonization of cement manufacturing. As India's GDP increases, one of the things that you can do is build very, very rapidly, which will mean more use of cement, which will mean more carbon dioxide, and that will hurt. That process, 35% of carbon dioxide used in calcination. Here, we have to replace fossil fuel by hydrogen. And that is one of the work that we have said that we'd like to do over the next year to year and a half. Demonstrate that it's possible. Start working with construction industry. We're already working with them. They are very keen that we are doing this. 65% of carbon dioxide is emitted during calcination process. Now, this is complex. What can we do? Because this carbon dioxide will be emitted. We have to capture it. Now, what do we do once we capture this? Cement plants, by the way, are located in about 6 regions of the country, because that's where the limestones are. And their carbon dioxide is going to generate. We don't want them to just go out. So, one thing that we have figured out, that since we use the cement to make concrete, can we sequester the carbon dioxide into the Fortunately, we have the technology. The only, of course, one problem there is that if you put carbon dioxide in the concrete block, which we can do today, it will go and hurt the embedded steel rods because they will rust quickly. So we have to replace that by alternate materials like glass or carbon composite. There also the work is going on. Same time, the concrete thin walls. Instead of glass walls, we can make walls as thin as glass made out of concrete. And this can be done. It will help us tremendously. First of all, we will not use bricks. Bricks take the topsoil from our agriculture. We can replace that by thin glass-like concrete. And this does not even have embedded steel rods. So sequestering carbon dioxide in it can be done today. What will be the problem? The only problem is, how do I take carbon dioxide, which is generated in different parts of the country, and bring it where concrete is going to be? Concrete will be done where stones are available, but near the site of construction. And it has to be at least at 1,000 places in the country. So at 1,000 places, we need to learn to put sequester carbon dioxide into those concrete and do it commercially viable. And this is the challenge that we will take up. And we have people like Mr. Gergetu or Manu in IIT Madras, along with people like Arun, Satya, Rajneesh. I think we can actually do this. All that I will say, that India and the world needs to move to net zero very rapidly. As I said, instead of trying to sort of go after governments, also spend more, and basically we have to. Who have to work at? Our scientists have to work, number one. Our industry has to work. Those who have money has to work. And this is the relationship that we are trying to build and say, we will get things done, help government, get things moving, even faster than government. And we'll not even depend. We'll of course be right policies from the government. And we'll go and suggest and work with them to get the right policy. IIT Madras Research Park and IIT Madras is the top of all the technologies. And of course, it will require a very strong collaborative work. And this is something that we are building the culture at IIT Madras. So we are not talking about I, we are talking about we, and we will get this there. Approach to show that we'll validate the technology and economics by pilots. And we'll raise money, whatever money is required for this. And then commercialization and scaling will follow from startups, from established companies and all. What is our request from France? We are seeking partnership with academia, industry, and startups in Europe, especially in France. It will help us accelerate. If you see one area, I didn't say that we are strong on is nuclear. But I know we need to start doing some R&D. small modular nuclear. We're not talking about large plants. This will pretty much complete. I want to point out only one more thing, which was mentioned in the morning, and which I should have included. We are also, my person who's working on agriculture is somewhere, must be sitting here. We are also working on agriculture. Agriculture's emission, usage of carbon emitting technology will not be even there without hurting our farmers, because they come at the lowest end of our income bracket. We need to somehow work with them to see that we don't emit more carbon dioxide. We are very committed to this. And it is here we are looking at partnership from Paris Saclay as first, and then from Paris Saclay to the rest of the Europe to help us get there, because you will not just help us, you will help the world. And remember that when we do it, there are many countries like ours. I think Africa will have a very large population tomorrow. Their GDP will grow. They will start emitting very large carbon dioxide tomorrow if we don't start acting today. In some sense, I'm looking at European and India partnership as a third pole. There is something being driven from China, something being driven from the United States. But India and France partnership, India and Paris Saclay partnership, India and Europe partnership, with our R&D and industry can provide the third pole. Thank you very much. I don't know whether I
thank you, Professor. We thank you very much for this very huge challenge that are just that India is going to face and to deal with, will have to deal with in the coming years. We have time for a couple of questions. I received already some, so waiting maybe for some others. I will try to start with this one. You have mentioned hydrogen, but you have mentioned it linked to, looks like fixed stations, linked to facilities, factory for the cement. What about hydrogen regarding electromobility? I mean, first train of hydrogen has made some trials some time ago in France, buses with hydrogens, and some cars also, some taxi brand have got some hydrogens. Is it something that could work for India?
So I have worked on electric vehicles and to some extent driven the electric vehicle movement within India. 5 years back, I had gone to Delhi as a principal advisor to Piyush Goyal, and actually I formulated the electric vehicle policy. Now, you know, Indian electric vehicles are very different from that of the world. Indian electric vehicles are small. 80% of our vehicles are 2 meters. We travel very short distance a day. 3 to 4% are 3 meters. Many of you drove this 3 meters. We have 14% cars, but out of those 14% cars, 85% of those cars are under rupees 1 million. And they are very small cars. We don't need hydrogen for it. I think lithium-ion battery will do very well with motorcycles. For large buses, large trucks, long distance trucks, and maybe some very large car, hydrogen may be required. I don't know. Will it be hydrogen? Will it be lithium-ion battery? I don't want to predict. We are anyway going to work on green hydrogen. So we are, in fact, one of the projects, if you saw, was use of hydrogen. We'll try it on a three-wheeler to drive the vehicle. We'll learn that. We will have full grasp of the project. But let me tell you, since I do work on technology and economics, today our lithium-ion battery cost about less than 15% of what a green hydrogen vehicle will cost in terms of operation. Of course, green hydrogen cost has to fall down by a factor of 3 times. Once it falls by 3 times, sure, maybe it is doable in the trucks, particularly the long distance trucks.
Thank you. Thank you again, Professor. It was very inspiring, and I'm sure a lot of opportunities will come in the mind of our attendees, and that, as you said, this collaboration should be very fruitful and lead academia to come closer to Indian institutions. Thank you very much.
Thank you, and I'm signing off. And
Yep, I'd like to invite Madame Christelle Laberty-Robert for the following speech. Christelle, the floor is yours.
Yes, thank you very much for the introduction. Can you see my screen?
Yes, it's okay.
Yes. Okay, so thank you very much. I would like to thank Sylvain Franger for the invitations to this Indo-French workshop on sustainable energy. So I will start my talk by speaking about the RS2E competence cluster and its roadmap. And I will be finishing with some work that we are running in the lab. So the RS2E network is a French research network on electrochemical energy storage and is edited by Jean-Marie Tarascon. So I will make first a quick description of this network. So it has been created in 2011 by the French Ministry of Higher Education, Research and Innovations and the CNRS. It gathers 17 research laboratories, 14 industrial partners, and 3 public enterprise specialized in tech transfer. RS2E in figure, it is an annual budget of 1.3 million euro, 12 postdoc and PhD funded by years. It's more than 120 peer-reviewed papers and 24 active patents family and 2 spin-off, Tiamat and Sphere. So our research focus on the core competencies of RS2E laboratory. So there are 5 work plan. So one is on advanced metal ions. The other one is on battery sensing and self-healing. There is one on capacitive storage, and another one on eco-design and recycling, and the last one on interface, aqueous and non-aqueous electrolyte. So besides these core competencies, there is transverse axis. One is on the theory, the other one is on analytical platform, and the last one, it's on prototyping transfer unit. So besides this different work plan, we have also some task force. One of them is on the sodium ion batteries that has been launched in 2012. The idea was to build a sodium ion battery based on the development made on the 6 laboratory. The first prototype was in 2015 with, as you could see here, with quite good cycling. And because of this good result, Tiamat has been created. Sorry, it's a little bit too fast. And the idea in 2018, and the idea was to work on the materials, electrolyte innovation, and engineering. So the Tiamat performance outlook is the following. So in 2017, they built the first cell with a power density of 19 watt-hours per kilogram. And the idea is to go to a much higher power density, so 150 watt-hours per kilogram. So the idea is to move from NVPF polymorph to the sodium-based oxide. So the motivations to make this sodium ions technology is because those systems exhibit a high power rate, 0-volt storage, and good sustainability and low cost. And all these attributes make that this technology can find applications in various markets. So here you have the targeted market. So it could be portable, electrical mobility, but also grids. And lastly, one of the targets is mild hybrid. So there is another task force, which is mainly focused on the solid-state battery that has been launched in July 2019. The idea here is to work on the different interfaces of this solid-state battery. In this task force, you have 10 laboratory and 3 company. Company are Blue Solutions, Bolloré, Umicore, and Saint-Gobain. So the strategy is to engineer the interface by doing a specific design. So here the idea is to do a heterostructure interface. The first prototype that we envisage is to explore sulfide electrolyte rather than the oxide electrolyte. The motivations to do this, it's based on the capacity of the sulfide electrode that has been developed in some laboratory. As you could see here, if you compare capacities that you can achieve with a sulfide electrode, the energy density, it's much higher. It's 5,400 watt-hour per kilogram. So the roadmap of this solid-state task force, it's first to build the first prototype in 2022. As you could see here, the prototype is made on argyrodite and LPS electrolyte. The main challenges are to master the electrode interface with argyrodite and LPS electrolyte. For the positive electrodes, one strategy is to coat the LTFS with some, I would say, the NMC oxide. The other strategy is to master here the LPS, the electrolyte interface, by using a different type of negative electrodes. So one of them is indium-lithium electrode, and one of the strategy is to use the anode-less electrodes. The second prototype is envisaged a little bit later. This second prototype is made on oxide-based electrolyte, so it's a garnet-based. The idea first is going to be the material selections. Material selection for the electrolyte, but also for the positive electrodes. And the second challenge is to master the interface between the electrolyte and the electrodes. So one of the strategy is to make organic, inorganic, composite electrolyte, and to also is to coat the positive electrodes, but also the electrolyte in the composite electrodes to avoid any chemical or electrochemical reactions. Regarding the negative electrodes, so there is a strategy to build here a specific, I would say, the buffer in order to have a good interface between your electrolyte and the lithium electrodes. So the last task force concern green batteries. With a strategy, a specific strategy on recycling and eco-design. So this task force has been launched in July 2020. As you could see, 4 laboratories and 4 companies are involved. So companies are Umicore, Ineris, and IFP-EN. The strategy is to rethink the recycling process and in order to favor one-step recycling and to have a direct method. So that's the first strategy. The second strategy is to rethink the self-configurations and to make a Lego type battery. So the idea is to make a battery that you can disassemble, and then you can take, for example, one part of the battery and you can use it to rebuild a new batteries. And the objective of this task force is to make a battery that is 100% eco-design and 100% recycled. in the work program on the sensing and self-healing in batteries, the idea is to to increase the performance of the batteries and to increase also the lifetime of the battery. So the idea is to avoid all the secondary, I would say, reactions, or to avoid degradation of electrodes when you are running the batteries. And the idea is to cure the batteries. So the strategy to do that is to identify the failure mode via sensing and to add some self-healing functionality inside the batteries. So the self-healing functionality will be bring through the membrane, through the separator. So here the strategy is to functionalize the separator with a different type of functionality in order, for example, to avoid cross to avoid that metals that are dissolved at the positive electrode go through the separator and to destabilize here the SEI. The other strategy is to develop specific self-healing polymer in order to limit cracks that could happen in the positive or in the negative electrodes to avoid the loss of electronic percolations. So in the sensing directions, so the strategy right now is to inject optical sensors. So here you have some results. Here, what people have done, they have followed the modification of temperature inside the cell during the charge and the discharge of the batteries. And what they have seen is that you have a change of the temperature inside the cell, and those change of temperature could be linked to formation of SEI or to some phase change inside your batteries. As soon as you have a clear idea of what's going on inside your battery, you can develop some self-healing processes. And as I told you, one of them is to make a smart membrane. So here you have some example of work that has been done on cyclodextrin. The idea was to functionalize the separator with some cyclodextrin, and those cyclodextrins, they change, I would say hydrophilicity with the temperature, and you could trap some components, I would say some species inside your battery. So here, this has been done on the lithium sulfur battery, and the idea was to trap here a polysulfide by using this cyclodextrin. This work plan is to inject intelligence into the battery to reach optimum performances with the idea to push back the pivotal recycling age and to allow second life of the batteries. So in my lab, so I'm working at LCMCP. It's a lab that is belong to Sorbonne University. So we are interested in modification of separator. And in these directions, we are making fibrous membrane, and those membranes, they are made of fibers. Those fibers, they are made of two components, PVDF polymer and a silica network. We use the silica network to graft some specific functions on top of the separator. So here you have some strategies that we have developed. We use a sulfonate group to exchange proton by lithium, but then lithium by some transition metal. We use also some other type of functions. So here you have amide functions in order to trap metallic ion. So we use different strategy to graft this functionality on top of the separator. So co-condensation, post-graphing, and encapsulation for example, here terpyridine. here you have the different fiber morphologies that we were able to achieve. And what is very interesting for this membrane is that they exhibit quite excellent thermal behavior compared to, I would say, regular separator. So when you heat it up here, your membrane, you don't see any change of the morphology of your membrane. And if you look here at the microstructural level, I would say, there is no change of the fibers morphology, which is not the case if you heat it up your PVDF HFP, or if you heat it up, I would say, the regular separator. So those functional membrane has been tested in, I would say, the classic batteries, which is made with a different type of, I would say, the high voltage electrodes, positive electrodes. So here you have one example with LNO electrodes. And what we have seen that some of the functionality are much better in terms of, I would say, metal transition trapping. So for example, here it was a terperidine function that was much more efficient. We are also involved in the solid state battery task force. And our strategy is to avoid or to control the reactivity between solid state electrolyte and cathode active materials. So in these directions, we have two different strategies. One of them is to make a composite electrodes, and instead of coating the positive materials, that's what people usually do in the literature. In our case, we are coating the electrolyte in the composite electrode, and the idea is to protect all the interfaces. By doing this, you protect the interface between your carbon electrodes and your electrolyte, but also your electrolyte and your your electroactive materials. In the same directions, we are developing low sintering processes in order to limit the reactivity between solid electrolyte and electroactive materials in your composite electrodes. And we developed cold sintering processes. Here you have some example of sintering of the garnet phases. And you could see that we are able to sinter these materials at quite low temperature, so 120 degrees C, for, I would say, a reasonable time. So it's about 1 hour and 30 minutes, and by using pressure. In fact, this process is based on the dissolution and precipitations of your materials, which is encouraged by the temperature and the pressure. So here you have some, I would say, impedance spectroscopy result, where you can see that by playing with formulations of your LSZO pellet, you can reach different type of conductivity, and so we were able to achieve the conductivity value that you get when you go to very high temperature. Okay, so I will be finishing my talk to say that there is probably many opportunity for collaborations between India and France on different topics. So one of the topics could be development of materials and electrolyte and modeling. Another one could be on interfaces and more specifically on in situ characterization technique. Maybe collaboration could be done on the sodium-ion battery and solid-state battery, but also on development of smart batteries. So I would like to thank you for your attentions, and I will be very pleased to answer questions.
Right, Christelle, thank you very much. Thank you very much for this this presentation. I have received few questions, but I would like by text. I would like to see if some people are live would like to ask some questions first. Otherwise, let me start. One of the questions we receive are, considering the recycling process is cost compared to bare element, isn't it a break to the development of a viable solution?
Yes, I mean, there is, in the recycling aspect, there were two strategies. One of them was, I didn't speak about that. It was to support industry right now on the current recycling process, which is pyrometallurgy and hydrometallurgy. But those process, it's costly in terms of, in the sense that you are using electricity. I mean, and also one of the problem, I mean, some of the problem of this process is you are producing CO2, depending on the way that you are using to produce your energy. So the idea is to really avoid, I mean, to make something much more simple and to try to limit this cost by trying to use technologies that you won't be dependent too much on, I would say, electricity, and also too much on the productions of CO2. And what people think, I mean, the strategy is to probably to try to redesign your systems in the sense that you will be able to disassemble your batteries, to take, for example, your one of your electrodes and to see if you can, I would say, repair it, and then to use again your process. So so it's to make it's to make something simple in terms of processing, but in order to limit the cost and to avoid, I would say, productions of CO2 as well. That's the two, I would say, strategy for this recycling idea.
Thank you. Thank you very much. We have time for another question. If one of you want to raise his hand or send me the chat box some information.
Okay, I've seen one question about Indian startup. Okay, I can, maybe you can send me an email and I will answer you directly, how we can collaborate on these topics.
Good. Regarding the self-healing batteries also, how, if you were mentioning to increase the number of cycles, how many, in terms of percentage, what do you expect to gain? 10% more cycles, 20% compared to similar batteries?
Well, it's difficult to say. Of course, we would like to have a large number of cycling. Well, I mean, for the self-healing, I mean, what we are targeting is, for example, one of the targets is to probably go to the use of silicon-based electrodes to make this system working. So that's one of the idea. For the, I would say, membrane functionalizations, the idea is to probably, I would say, see if we can really trap the, I would say, transition metal, and see if by doing this, we are really able to, I would say, increase the cycle life. So it's a very low TRL at this moment for this strategy. Of course, we would like to improve, multiply by a larger number, but yeah, it's difficult to say right now.
Okay, understand. And maybe last but not least, I was wondering, considering the people involved and your partners and researcher, PhD you were mentioning, have you got some of them working under industry academia contract, what we call a bourse chiffre in French?
Yes. So we have a mini Bourse Cifre. So we have a Bourse Cifre on sodium-ion batteries, on also solid-state batteries. So yes, it's something that works quite well in the network. Yes.
Okay, great. Thank you very much. Thanks again. I would like to invite now Dr. Koshalja and Mr. Anson Sando to do the presentation. Anson and Koshal, the floor is yours.
Thank you, FX. I hope everyone can see my screen.
Not yet. Not yet, Anson.
1 second. Can you see it now?
Still not.
You may not have shared.
Tejas, could you help with that? Yep, coming. It's good.
Great. I hope you can all hear me and see the screen. Firstly, a very good afternoon to our friends joining in from India, and good morning to our friends joining from France. My name is Anson Sando, and I'll be making this presentation along with Dr. Kaushal Kumar Jha. We're from IIT Madras Research Park and the seat IIT Madras Center. Now, the Industrial Revolution marked a major turning point in history during the mid-1800s to the mid-1900s. Almost every aspect of our daily life was influenced in some way. The transition included going from small groups to hand production methods to new machines, manufacturing processes, and in the energy context, the increasing use of fossil fuel to power this transition. A visible shift in the mechanics of our daily lives was evident for all to see. Today, on the other hand, we are witnessing another almost invisible shift in how we consume our energy. The transition to renewable energy marks not only a systemic shift in how the energy we consume is generated, but also points towards an energy revolution that is key to the very future of our planet. Now, what we can see here is the share of renewable energy capacity globally has doubled in the last 15 years alone. And what's worth noting even more is that 80% of all new electricity capacity additions in the world today was renewable energy based. In India, the story is a little brighter. The share of renewable energy has doubled in the last 5 years alone, and is today among the cheapest places for energy anywhere in the world, with solar and wind costing 2 rupees to 2 rupee 50 paise per kilowatt hour, whereas coal, on the other hand, also costs close to 2 rupee 50 paise per kilowatt hour to produce. Now, there's significant potential for solar and wind to meet most of today and tomorrow's needs, with nuclear, hydrogen, and ocean tidal, along with biomass, playing a complementary role. So what does it take to move towards 100% RE? Or what is it that we're missing here? In the Indian context, we look at the capacity versus generation tail. India's current RE capacity stands at 25% of the total capacity, whereas the total electricity generated from solar and wind stands at only 8% of the total. This is largely because of the plant load factor of RE-based plants, which stands at around 22%, whereas that for coal-based plants goes up to 85%. Or in other words, the ability to turn on or off at will simply reigns supreme. The challenges of intermittency and controllability makes RE not fully 100% available. This is where storage comes in and essentially makes it available on demand. Because renewable power sources are available only in certain hours and on certain days, and the output determined is completely by natural forces and cannot be controlled, unfortunately, by us humans. And that's where we see storage playing a significant role in helping bridge the gap, providing the much needed flexibility element, and also providing mechanisms to manage our demand, thereby helping us, importantly, to move towards 100% RE future. Now the question of how much storage is needed. Wind and solar, as I mentioned, is not controllable, leaving a big demand-supply mismatch. What I've plotted here in the graph is the estimated generation profile of a wind and solar plant on a daily basis. And as we can see, there's a variation in terms of when solar is generated, which typically peaks during the afternoons, whereas wind typically peaks during the evenings and late nights, causing what we call a short-term storage mismatch, which is essential to be bridged to ensure that RE is meeting most of this demand. And how much of storage is needed is essentially computed using the difference between RE generation and the estimate demand in a full day. The two kinds of storage that we're working on to meet the short-term storage requirements are lithium-ion batteries, as well as chilled water storage, which is essentially designed to meet the mismatch of a few hours to a few days. Now, on further or a deep dive analysis, what we also saw was as seasonal shift or seasonal variation that comes with both solar as well as wind. Solar, on the one hand, has a small variation that happens on a month-to-month basis, but wind, on the other hand, as you can see in this graph, is very seasonal in nature, where the bulk of the wind generated in a year is happening in 4 months, whereas there is a much smaller generation in 3 months, and for the rest of the year, which is 5 months, there's very poor generation. And this is why it's important for us to store large amounts of energy for months together. And this is where we need long-term storage, such as metal airflow batteries, and like Professor mentioned, zinc air and aluminum air is the two main types of batteries that we're working on here at the research park. Along with pumped hydro and compressed air storage, we're also looking at hydrogen storage technology, but that truly needs to come down in cost to make economic viability. I will now hand it over to Professor Dr. Kaushal Jha to walk us through the two kinds of storage systems that we're working on here at the research park. Over to you, sir.
Thank you, Anjan. So, what we have as India as an opportunity with us is something known as thermal storage. So, we know the water, which has the, if you see the property of the water, it has one of the highest heat capacity, and then also one of the highest latent heat. So in any form, either you wanted to use it as a sensible heat storage or latent heat storage. In both the case, it works well. The second good point about water is it's available. It's available in a quite good amount. And if preserved properly, like if rainwater harvesting and other things is taken care, we'll never have a shortage of water. And when we run this type of system in closed loop system where there is no evaporation, there is no wastage of water, and this works in that case in quite good shape. Why it is chilling or maybe heating? So in any typical commercial complexes, in fact, even if you're staying in home or like during what happened during the COVID time, around 40 to 50% energy is being used only for heating and cooling applications. It's basically you're maintaining your surrounding for your comfort. So almost 40% of the energy, and that 40% energy from where it is coming right now, it is coming from the grid, or that grid is basically mostly with the fossil fuel. Now, if I have to increase the RE footprint, then if somewhere like the controllability factor which comes, and if I can store that energy either in a cold form or in a heat form, then I can reduce the dependency. Wherever there is a peak, I can store. Whenever there is a shortage, I can always put back to the system. So for that, the thermal storage works out to be very well. In what we have is a 0.3 million liter system here available. And in that, we chill the water to 6 degrees centigrade. And that's how we circulate to the offices. There is another heat exchanger, water to air heat exchanger, and that sends the air, cold air to the offices building. The same water, whenever there is excess RE, we store in our one storage tank. The only problem with that storage tank is that right now, since we have not a sufficient insulation duct, it's a bare metal storage. So there is a chance of 0.5 degrees centigrade temperature rise every hour if I don't use it, if it's just stored. So, and can be used up to 20 degrees centigrade. So it could still take almost 35 to 40 hours to make it useless without using it. But generally in every 3 to 4 hours or 5 hours, we use it so that we can take back all the energy what we have stored. And as you see the profile of wind energy as well as solar energy, it peaks, the solar peaks during the midday, wind peaks during the evening, and whatever the gap period is there, that time I can use, and during those peaks I can always charge that thing. The overall average losses, what we have seen is around 5%, and that's mostly because of the additional pump which we run to circulate the water. The total heat transfer capacity, what we have, or heat storage capacity, what we have is 17,460 megajoule, and that's on heat energy side. Electrical equivalent of that is around 2.45 megawatt hour. And this is the electricity which we can store in that system. Now, what we have a chiller system. If I don't have a storage, that chiller system keeps on running based upon the load of the office building. Now, whenever there is a excess RE, I use the same chiller to chill the water in storage. And when we have the deficit in RE, at that time I use this chilled water in combination of chiller or without chiller to run our HVAC system. What we are also working on, that the same storage in Chennai, generally we have temperature between 35 to 40. We don't require heating, but some other places in India, or especially in Europe, where you require a lot of heating also. At that time, the same chiller can be converted as a heat pump with very basic modification, and that in that case, same water can be heated to 60 degree or 70 degree and can be kept as a heat storage in such cases. So the chiller, which acts as a heat pump as well as a chiller, and then chilled water storage, the places like India, and then the same thing can be used as a heat energy storage in the places like Europe or cold places. So this is about sensible heat. Now the capacity of this system can be easily increased in multi-folds, in fact in an order of 10, by using a latent heat, by utilizing the latent heat capacity of that. Problem is that if I put water into ice that goes around 0 degrees, the energy consumption of chiller, the storage chiller, whatever is available commercially, becomes very high. So it's good to have something which can still use the latent heat capacity, something like hydrate, phase change material. And I may not like to go for 10 times or 100 times of the capacity, maybe 2 times or 3 times or 4 times. So a small portion of hydrates circulating inside the chilled water tank, and that increases capacity 2 times or 3 times or 4 times. So I can have, with the existing setup itself, the energy storage capacity maybe 2 times, 4 times to 6 times. So multiple use cases for comfort, heating and cooling both is required. For industrial application, industrial, commercial and domestic, where I can use even the heat pump application, which is chiller is essentially a heat pump also. A chilling capacity can be used for the comfort as well as the heating portion which has gone off, getting wet, I cool it through a water cooling tower or something, can be used as a process heat. In that, the system COP increases to 5, 6, almost 5 times to 6 times. So multi-use cases. Now, the next thing what we are working is lithium-ion storage system. Another point about the chilled water system, it's comparatively quite cheap compared to any other storage system. Flexible, handy, can be placed at anywhere. Another system what we are working on is lithium-ion battery storage system. Essentially, similar background of EV. Some small modification, capacity becomes very large. The cell, then parallel and the series combination becomes module, and the module becomes strings of some particular kilowatt hour. What we have been working is something between 250 to 500 kilowatt hour, independently managed through BMS, and then multiple of this will become in parallel to create a megawatt hour system, and many multiple of such megawatt hour systems connected together become a gigawatt hour or 20, 30, 40 megawatt hour system, which could be helpful for places like ITM Research Park. Since what we are also looking for that it's act as a storage system, so it should give capacity, or it should give the energy to 3 to 4 hours. So essentially the charge and discharge rate is around 0.3C, 0.2C, 0.4C or 0.5, not more than that. And in such cases, a properly air-cooled system is sufficient for the cycle life or calendar life of the battery. Then there is a bow-out item of battery converter of large capacity, 750 kilowatt hour or more, which can connect with the multiple battery banks of 1 megawatt or 2 megawatt megawatt hour capacity to provide the energy whenever there is a deficit in RE. Whenever there is access, the same system will keep on charging the battery. Then another is power conditioning system, which gets attached to that, which conditions to the power, condition power to whenever it's required in the grid, the similar frequencies in synchronization, and all those things can happen. And then the same system is connected with the utility inside the commercial complex. It has a very robust firefighting system, 2 layers. One layer works with the thermal management system itself, and the second layer, if anything goes further wrong. And on and over that, there is a robust energy management system which keeps on tracking each and every element from cell to module to string to BMS, power conditioning system, bidirectional converter, as well as the energy input from the grid and out to the utilities. We have smaller battery packs of 100 kilowatt hour, 200 kilowatt hour. So we have made several such packs and placed in the several locations in India where we keep on getting the data. And one of such packs we have made in our lab to check each and every functionality of this at a prototype level, as a pilot experimentation level. In a couple of months, we will be moving towards 2 megawatt hour battery pack. Now, the cost, that becomes very important, the cost of storage. So the capital cost of storage per kilowatt, that's what is important. It depends upon how many times we are charging and discharging the whole thing. If we are doing it 1 time or 1.5 times and 2 times, it comes out to be around between 1.5 times to 2 times, it comes out around 2.5 rupees, 2.5 per kilowatt hour. Now I have energy available at 2.5 rupees per kilowatt hour. This additional 2.5 rupees per kilowatt hour, and then some wheeling charges and the maintenance and other things brings it to around 8 rupees per kilowatt hour. That is what Professor was saying in the morning. In fact, this is for lithium-ion battery. The chilled water system comes much lower than that, on larger scale. It could be something between 1.5 rupees to 2 rupees per kilowatt hour. So thermal storage, it's approximately 50 to 70% cheaper, both in capital as well as on the running cost. How many cycles battery charge and discharge can be used per day? For lithium ion, typically not more than 2 to 3. But for thermal storage with chilled water can be done multiple times, depending upon the energy availability and energy deficiency. There are losses in lithium ion. We are trying to make it should not have more than 5% losses in round trip efficiency. Chilled water, depending upon the outdoor temperature or the heat losses in the storage, should not go more than 10%. So that's what we have set our target. The effective cost per kilowatt hour usage. This has been what we are talking about has been calculated considering the depreciation as well as the the interest rate of the India, which is around 10 to 12% per annum. Plus environmental impact, toxicity, hazard, recyclability of the material used. So I was talking about energy management system. In energy management system, what we are trying to do is trying to map each and every data from renewable energy generation till consumption. And that we have put as an energy national energy dashboard. This tracks, maps, and monitor all types of energy generation, storage, as well as the consumption. Integration of multiple sources. So one way we have rooftop solar, other way we have the grid solar, then we have grid wind, then we have, since we cannot consume 100% today, so some percentage it will come from the fossil fuel also, so that grid, lithium-ion storage, then whole the chiller HVAC system, room lighting, and then air distribution system, everything together that becomes a part of energy management system. This helps us in optimizing the energy usage. If somewhere people are not available, do I need to run the air conditioner, or do I need to send the chilled air that side? So if it can sense, it closes that particular ducts and vents so that energy can be optimized. So all such type of sensors we are trying to integrate, and wherever it is not available, we are trying to put so that we can optimize the energy consumption or improve the energy efficiency. The technology readiness and economic, the IIT Research Park, which is around 1.2 million square feet space available, is the showcase, a place where we are showcasing the whole project. And once it is done, I think it would be easy for us to deploy it across such commercial complexes, initially in the India and then across the world, along with the economic viability towards 100% renewable energy. So thank you. If there is any question, we would be ready to take it.
Thank you. Thank you very much, Kaushal and Anson. Is there any question coming from the audience? I've received one already, but there was one question regarding the process of thermal exchange, which is slow in terms of calories compared to battery storage. Is there some limitation in terms of surface, in terms of volume? And could you, just for people who are not familiar with IIT Madras Research Park, give an idea on what is the global surface of the building where this system has been tested on?
On the global sources. So thermal storage system is, yes, it's not as fast as lithium-ion storage, but the application what we are talking about is much better in that application than lithium-ion storage, because what we are doing here is storing the form of energy what we are going to use immediately. So in HVAC application or heating or cooling application or heating or ventilation application, the same form of energy is being used. So that's a plus point for that. It's all about in what type of energy where we are using. So we are trying to store energy in the same form which can be used in the same form.
What are the area, the room sizes which are total?
So we have around 1,000 square feet room to around 4,000 square feet room. At some of the places, it can go up to 10,000 square feet room, what we have. And total area covered is 1.2 million square feet.
Okay, thank you. Thank you very much. We are running a little out of time, so we'd like now to ask Samantha Hilliard to come and to join.
Hello, everyone. Let me share my screen.
Yep. It's coming.
Okay. So you see my screen all right?
Yes, all yours.
All right. Thank you already for letting me have this opportunity, and thank you everyone for attending today. Today, I would like to address the technical challenges of hybridization and storage, especially for the decarbonization at Total Energies. I'm currently working at the R&D power lines in hybrid and storage part of Total Energies, and we have many obstacles in front of us, as Total has announced officially that they aim to reach net zero emissions by 2050. Nevertheless, this complexifies the portfolio and future portfolio of Total, as this essentially complexifies the existing and future systems. Naturally, we would like to decrease, of course, fossil fuels and increase renewable energies. And to do that, we have many obstacles in our path. So a few, I would say, topics or subjects that we would like to address in the near future are, of course, smart buildings, management systems, essentially for environmental purposes in the end run, risk mitigation for off-grid hybrid power plants, of course, because this is important in planning and deployment, operation of these hybrid power plants on grid and off-grid as well, microgrid management for other applications, which may be kilowatt to megawatt. And finally, the power orchestration of these distributed energy resources, how we manage our portfolio of increasing renewable energies with the merchant risk inherent in ever-changing electricity markets. So to address these obstacles, we have started to build a large, I would say, project and subjects, activities and collaborations regarding modeling, simulation, and of course, power, hardware, and loop, which is the ultimate step. So these activities enable us to digitalize the existing, I would say, renewable, hybrid, and thermal systems, so that we can safely and I would say precisely model them, simulate them, and understand if these model simulations are correct, far off, or what, so that we can safely, away from these high voltage and I would say risky environments, test these systems and ensure that they are stable before deploying them. So for modeling, we are looking currently at several storage technologies, but more specifically battery characterization, lithium-ion. For the moment, as Total Energies, we have, of course, our affiliate Saft, who makes batteries for us. And then the simulation, as we know very well, oil and now we're learning more into gas, renewables, and especially storage alongside Saft. So simulating these systems for the purpose of decarbonization can help us attain this net zero 2050 in a timely and safe fashion. These simulations should ideally facilitate and accelerate the decarbonization. Validation of these models should ideally be done with field data and potentially pilot data if we have no field data from that, or even publications or previously collected data. And then finally, this power, hardware, and loop, which I will be discussing in detail later, which refers to real-time data collection using hardware and software combined, which we can enable rapid control prototyping, which can help us for the battery management system, the power management system, and of course the energy management system, all levels of the control hierarchy, and ultimately enable us to have these real-time simulations at several different levels that we can ensure stability, reliability, and safety for the facile and accelerated deployment and retrofitting of these systems. So in terms of modeling, we have three different models that we would like that are in our I would say digital portfolio. This high level model is I would say more simplified and works at 1 hour time steps with the project lifetime, years that we can go throughout the lifetime. And this is essentially a good choice for model validation at the PQ response control system. Even more precise and then that would be the mid-level model, which is more energetic models, we would say. So these are more at minute time levels and can be associated with, I would say, more energy management system strategy in order to ensure that. And so, of course, these are slightly more defined and accurate and detailed than the high level model. And then finally, the low level model is where we dig into millisecond and analyses and events that occur, which we can understand stability, how the behavior of these assets within these hybrid systems. And so this is the ideal time step and choice to analyze faults, transients, switching losses, and other very detailed electrical engineering aspects of these hybrid systems. So with this three levels, we can essentially do feasibility studies for more high-level business actors, and then mid-level studies for more sizing and planning of systems, and then finally low-level for the detailed planning and risk mitigation. And so how are we going to do this? The digitalization within the R&D group is surely aided by SAFT. So SAFT has been working on batteries for years and years and years. They're well known in the entity. And so with them, we're working on battery characterization to understand at the cell level, and then the module level, the rack level, container level, and beyond that, as there is active balancing and many nuances that go in with the battery management system. From this, we can build models, the battery being electrochemical, physical, whatever we would like. And then with these three levels, the high, low, and mid, and then scale up, I would say scaling up from, cell level to module to rack to container to megawatt to gigawatt. So we build these models based on battery characterization with SAFT. There may be different entities, the cell, the container, and then applications for decarbonization that we have identified based on our existing assets, as well as future potential applications and projects we can build around the world. And then finally, the layer of control. So understanding these three levels on our scope is important, because then we can run these simulations to understand how the system reacts. From these simulations, how do we know if this is actually going to react like that in the real life? Well, from pilots and existing systems, we can collect a lot of data, big data, things like that, so we can have more and more understanding of faults, sizing errors, and really refine our strategy in terms of deploying renewable energies and retrofitting these fossil fuel areas. So these results in validation are essentially validated versus real and simulation data. We can also do this via power hardware in the loop, real-time data control, and rapid control prototyping. So finally, how do we verify and validate this? So the business requirements, of course, drive our activities. So from there on, we can understand how to design the system. If it's a retrofit, if it's a new fit, if we have to integrate storage, increase photovoltaics, and from there we can model the system at the high level, mid-level, and low level. From then, we can go into unit testing, testing each individual asset, integrate them into the system testing, and then finally, this power hardware and the loop acceptance testing will give us simulations that we can really understand, and we can feed that back into the business units and strategy to understand if this really does meet their requirements. So to understand this power hardware in the loop, this battery system that we've actually planned a power hardware in the loop bench test at Saclay to begin at the Institut Photovoltaïque de France. So this power hardware in the loop system is essentially a bunch of simulators and amplifiers that are connected to real hardware elements. And so this way we can physically install a battery, thanks to SAFT, to be integrated into this small microgrid. And so, of course, when we talk about stationary energy storage and understand the megawatts and gigawatts necessary to deploy in the future, the lithium iron phosphate batteries have taken the scene for stationary energy storage due to their, I would say, less tendency to thermal runaway and lower price. This way, connecting to this battery to these simulators and amplifiers can enable us to collect real-time data. And so we would have to modify our dynamic models to be in the same time step as the real-time acting microgrid. And with this, these various simulators, amplifiers, hardware, software, we can have various configurations. So we can test gensets, gas turbines, wind, PV, load grid, and these can be either simulated or in hardware. And this enables us to safely test these systems, as before people were in high voltage areas, and to test these simulations, it's a very risky situation. Here we can go from, thanks to the amplifiers, we can step down the voltage to I would say translate for the simulator, so we can work at lower voltages and have a safer environment. This also enables us, with all of these models, to have a rapid control prototyping at several levels, like I previously stated, the BMS, PMS, and EMS. So to get really into the details of our planned power hardware in the loop bench, we are currently working with Opal RT, which is one of the providers of hardware in the loop, modeling in the loop, and power hardware in the loop technologies. And so we have several phases planned for the next few years, but of course this doesn't stop here. There's a potential to connect to various other hardware elements and add amplifiers and simulators in the future. And so we have 2 lots to be deployed, one currently at the Institut Photovoltaïque de France at Saclay, and then we are planning an innovation and research center to employ smart grid batteries, EV chargers, and a really environmentally conscious research and innovation center. And so planned for that will be in blue, these elements here. Nevertheless, this, of course, may change depending on the priorities and changes which occur in the near future. But nevertheless, we are starting currently with modeling wind, PV, battery energy systems, the grid, any kind of consumption patterns we may have, as well as all of the thermal assets which are currently we're currently trying to mothball. So in this grid, we have a microgrid bus bar, and we have one simulator seen here tied to an amplifier. This means that we can have a load, an actual load, and this amplifier will translate the voltage to the simulator and then connect to the master simulator, which will relate all of these smaller systems over here. Of course, we can separate this bus bar, so we can do, I would say, experiments in parallel. So if we just wanted to test a microgrid of wind and battery and PV, we can disconnect these and then have maybe fossil fuel generator here, a genset here, and other things. But ideally, the first 5 phases touch on the most important priorities for us, which is the integration of renewables and understanding their interaction due to their variable behavior. So currently we have about 20 kilowatt peak of PV photovoltaic panels on the rooftop of IPVF. So we will physically connect these hardware elements into this bus bar. And so via these amplifiers and simulators, we can have a real photovoltaic, one of several of the strings or one of the strings photovoltaic panels that will participate in the simulation, a simulated grid and a simulated load. And we can see how these photovoltaics will react. We are also planning to deploy a 50 kilowatt, 100 kilowatt hour SAFT LFP type battery to do similar. And then, of course, wind, as it's a bit difficult to set up wind turbines, small or large. Of course, we're looking in the megawatt larger scale in the future. This will most likely be emulated, and so we can have simulation and emulation thanks to these Opal RT simulators. And so simulators would essentially mimic existing behaviors and configurations of real devices, but these emulators will essentially duplicate the hardware and software of these devices. And then finally, we will have a DC simulator to simulate DC, most likely photovoltaic devices, so that we can study power conversion systems. And so this is bidirectional inverters, rectifiers, to best understand the state-of-the-art technologies that are going on. And so this should occur over several phases. And in the future, we have even planned to connect to the EV charging stations that should be installed at the Innovation and Research Center. And so conclusions and key takeaways for us in our endeavor to decarbonize our assets at TotalEnergies is that this decarbonization demands a drastic modification of existing assets and systems. And so time is of a factor, and storage can really facilitate this. And we're currently digging in with SAFT to lithium-ion modeling and upscaling, and of course the operation and ultimate controls to efficiently integrate all this. Finally, Well, and then according to these modifications, storage adds complexity as it's a very flexible, I would say, asset. And of course, we know lithium-ion prefers certain cycling and calendar operation. And so taking this into account may help prolong the lifetime and essentially add more value to these systems as well. Therefore, modeling at various timescales at different levels provides great insight to the battery operation and the system operation behavior, degradation, and helping us plan in these renewable and retrofitting systems. And finally, the digitalization is becoming more and more important in the simulation of these systems, which enables safer studies and ultimate project risk mitigation, which is very, very, very crucial as we're going from megawatts to gigawatts in the future. Thank you. Any questions?
Yeah, Samantha, thank you very much. We got some questions. We've got one regarding the output, the capacity and power, or the output of the system.
Yes. The output of the system for the first lot is about 250 kVA or kilowatts. And then we should go up to a 0.5 megawatt in 2023, 2024.
Okay, thank you.
And that's it. Everything is working at the same time. We can always separate it in different parts in parallel.
Okay, so there's another one from Christelle. I will pass the floor. Christelle.
Thank you, Samantha. So I have a question regarding hydrogen. So you haven't said anything about adding hydrogens in the loop. Do you have some scenario where you think about that integration?
Yes, exactly.
Of hydrogen?
I've been of course discussing a lot of hydrogen currently. I would say we are looking at fuel cells a lot, and we're looking at electrolyzers, of course. In Saclay, as we're currently planning the building, it's kind of a question of where we can put these specific hydrogen-based activities. And I think for me personally, we have other projects and of course collaborations all over the world, and so we're looking into electrolyzers there with renewable energies. So I think it's more appropriate for fuel cells initially, and then we'll see. But yes, definitely, there's definitely hydrogen within the storage portfolio.
Okay, thank you.
Okay, thank you, Samantha. Thank you, Christelle. I think we have no more question. I will therefore ask next speaker to come, and I will ask also Anson to join me as a co-moderator. Anson, can you take the lead?
Yes, thank you, FX, and thank you, Samantha, for that insightful presentation. Next up, we will have Professor Arun Kumar Chandran from IIT Madras to walk us through his presentation. Over to you, Professor Arun.
Yeah, thanks, Anson. So let me just share the screen. Is it shared already?
Share, I think you have to share. You have to share.
Okay. So let me share the screen. Cool. So let me share my screen and it's
That one here.
okay. And let me pull out my slide. Oh, that's here. Great. I hope all of you could see my screen. Thanks, Anson, for the introduction. So I'm Arun. I'm a faculty in chemical engineering, and it's a great pleasure here talking to the Indo-French community. And my electrochemistry knowledge and learning started in France, in Toulouse. Apparently, I was one of the Erasmus Mundus scholars in France. So I was in Professor Tarascone's lab when he was in LRCS. And I've seen a lot of people or faces that are familiar to me, Professor Patrick Simon. So it's a nice interacting. It's nostalgia, feeling the France back again here today. Thanks for this opportunity. Great. So after my master's in France, I did my PhD from EPFL and moved to Berkeley for postdoc, then joined as an assistant professor at IIT Madras in 2016. So my group predominantly, oh, what is that? I think there should be one more in the middle. Oh, yeah, here. I think I should do this. So my group predominantly work on electrochemistry and photoelectrochemistry, and we do focus use this basic knowledge to work on solar fuels, specifically on green hydrogen, and that's what Professor Jhunjhunwala and the rest of the team at IIT Madras talked about. And we do have a small presence in carbon dioxide reduction to fuels. And on the top left, you could see, which is not related to electrochemistry, but I'm just keeping my solar cell knowledge alive. So we are working a bit on perovskite solar cells. And that too, a bit of funding comes in once in a while that bleeds into that domain. So we do work on that. On the top right, we work on, I'm showing the metal air batteries, and which is one of the prime driver for renewable energy storage at IIT Madras Research Park. And we work with a bunch of industry partners on the metal air batteries, including Ashok Leyland, which is one of the premier automobile manufacturers in the country. And before I get started, I think I need to thank my group. I have one of the largest groups at IIT Madras. So these are the guys who literally make everything possible. And good brains and good money is making everything happen. And these are the great bunch of funding agencies which are funding our research. And I should thank all of them before I even get started. And yeah, let me just go here. So this is something very interesting. I think all our interest and research started from one thing, that is decarbonization. In 2021, India was emitting somewhere around 1503 million tons of carbon dioxide. And based on the economic growth, and I think nice talks from Professor Ashok Jhunjhunwala and Anson and Kaushal, they said like the amount of energy that you're going to consume based on the economic growth and population growth, it's going to essentially double by 2042. So essentially our emission is also going to double by twice, from 1,500 to 3,000 million tons of carbon dioxide. And I kind of like this stabilization wedges, which have kind of attracted from Pakala and Saclay, the two nice guys who created the stabilization wedges. So we don't have a single solution to solve this problem. Essentially, I think we need to work with multiple renewable and non-carbon emitting solutions. And here I've split this into 7 wedges so that I can maintain the status quo, that is like 1,500 million tons of carbon dioxide emission in India. And so I have given 2 wedges to solar. So this is like, I have to generate 490 gigawatt by 2042 from non-carbon emitting sources. So if I've given 2, which means roughly 140 gigawatts have to be generated from solar by 2042. And the next one I've given is like carbon capture and utilization. Essentially, carbon utilization, it can be direct or it can be converted to fuels back again. If we have to convert that to fuels back again, we'll have to use solar or wind energy again. So essentially, I think even this third wedge is like looped to the solar. So I'm talking somewhere between 200 and 250 gigawatt coming from solar by 2040 at 42. So the thing is that solar energy is like, as all the other speakers talked about, it's kind of quite diurnal. We have to store that energy. That's where all of us are coming together at Research Park is primarily aiming to literally push this renewable energy storage as a primary driver. And hopefully after we achieve this energy storage at Research Park, it can also be taken as an example by other commercial buildings, and eventually it can be implemented there as well. And there are like 3 primary ways, which we kind of believe in. Fundamentally, one is water splitting to generate hydrogen. And I'm not talking about what way. It can be just electrolyzer technology, or it can be photoelectrochemical water splitting. Some way we have to use to generate hydrogen. And our conventional way is to store in batteries. And I think nowadays lithium-ion batteries and lead-acid batteries are fairly predominant. And so we are moving into the next generation metal air batteries. Carbon dioxide reduction is still at a very nascent stage. And I think it might require like 10 years down the line probably to see the commercial reality for converting the carbon dioxide back to fuels, so that we keep the carbon dioxide loop constant and not increase the carbon dioxide significantly in the atmosphere. So just I want to quickly highlight and show the results that we have. In fact, like we work on photoelectrochemical solar water splitting. After this, I'll talk about metal air batteries quite much. So in the photoelectrochemical system, one of the fundamental problems is that a semiconductor that is stable in the electrolyte medium, that is one of the primary issues. And it was a serendipitous discovery that we found one of the vacancy out of perovskite. All of us know the perovskite materials are fairly known for high efficient solar cells, but then the moment we take it outside in the ambient conditions, they decompose instantly. Here, there is a class of perovskites called vacancy-ordered perovskites. It contains platinum. At the moment, we can argue that platinum is expensive, but I think we have to start somewhere and learn from these materials and eventually design materials to remove these noble metals and move to low-cost transition metals. The good thing about this metal is it is stable in all pH conditions. You can dump it in pH 1, pH 14, and it absorbs the entire sun spectrum. And we have demonstrated the successful water splitting with that. And there are like 2 papers that are published in the last 1 year time. And this is something I think will be taken as an example. And now we are trying to understand why this material is so stable. And once we understand that, I think we are also in the process of replacing platinum with other non-noble metals and then try to understand their stability as well. I think we are not married to the conventional A, B, X3 type perovskite systems, which give high efficiency at the moment. There is a second class called vacancy-ordered perovskite, which also significantly absorbs the sunlight spectrum. In fact, this metal absorbs up to literally 980 nanometers. It means the entire visible light and into the near IR region. So I think that this one can probably a revolutionizing thing in the future. And we were also working on water splitting system. And again, it's a serendipitous invention. We landed up in a light emitting system where we created distortion in a specific perovskite material in order to increase the excited state lifetime to increase the overall water splitting efficiency. That was our initial target. However, what we found out is that while we created distortion in a class of material called halide double perovskites, we found that the excited state lifetime go from somewhere between nanoseconds to all the way up to milliseconds. I'm talking about 6 orders of magnitude increase in the lifetime. That at the time, we also found these metals emit quite a lot of white light. Here, it's just an example being shown on the bottom right. And this work got published quite recently in Communications Metals from Nature. And this also attracted India's highest technology translation award, because this is one of the very stable white light emitters. And that's in fact 8 times brighter than the conventional white light emitters you see in the floodlights that you see typically based on the cerium. Yeah. And the most important thing, batteries for electric vehicles. Professor Ashok Dindwala talked about zinc air batteries quite much. And our work started not for stationary storage, but we started with electric vehicles. The thing is that India, at the moment, lithium-ion batteries are the really hot things, and they are the very viable technology. But then in Indian context, we also need to look into what is next for Indian vehicles or Indian energy storage. And we did a thorough analysis of all the energy technologies available. And of course, sodium-ion is one of the next thing. But then in Indian context, I think all the basic battery materials and then fabrication is all patented. And essentially, for all we want to do something, it's just like literally replicating that here. And we won't develop any in-house development and develop IPs in India, indigenous development. And that's where we stepped down to the metal air batteries. It's not just a random selection. Metal air batteries can be the next generation batteries for the electric vehicle technologies in 2 sectors. One is where there is no demand for high power, especially 2-wheelers and 3-wheelers, and the city buses, because they don't drive for longer distances. And this is also a mechanically rechargeable system. We have developed prototypes already in our laboratory. So essentially what it does is it's similar to the Lego block chemistry that one of our previous speakers talked about. So we just essentially, we spin the zinc and then we pull the zinc cassettes out, insert a new zinc cassette in, and the vehicle is ready to go. And then the spent zinc will be recycled using separate electrochemical banks using solar power. So essentially we are going to try to maintain the net carbon zero thing with that electrochemical recycling bank as well as with the metal air battery technology. And there is also one more indigenous reason, which I'll talk about in a bit. And we also work on large-scale carbon dioxide electrolyzers for converting to syngas and formic acid, which is a small presence. We don't work quite heavily on this. With that, I'll step on to my battery business. A typical metal air battery typically has a kind of positive electrode, which is based on oxygen, which we consume from the ambient atmosphere. And the negative electrode is some metal. And this metal can be anything. And we consume oxygen to generate hydroxide during discharge and the metal oxidizes to give electrons. And during recharging, I think the opposite reactions happen. It's a very simple system and it is very well known. I think people really worked on it for several decades and it's not a new technology. Essentially, we are trying to reinvent the wheel and fit it into a new vehicle. That's all what we're doing here. And if you look at various metals that's possible to be used with this technology, it ranges all the way from lithium, sodium, potassium. Of course, these 3 guys are unstable in the aqueous medium. I think they'll essentially blow up in no time. However, there are other 4 different systems which can be stable: magnesium, aluminum, zinc, and iron. You could see that the energy density, for example, its specific energy of aluminum is like 5779 watt per kilogram, which is comparable with lithium. And so do, like, if you look at the zinc, well, this is like fairly low. And however, like, there are other numbers are fairly comparable to the lithium. It's not like far away from lithium. Essentially, when you look at the lithium, both the specific energy, volumetric energy density, are comparable to lithium when you look at aluminum. However, for zinc, it's fairly low. But then in the real devices, aluminum don't perform as well as zinc actually. So zinc is still the best performer among these class of metal air batteries, that aqueous metal air batteries. The biggest advantage of aqueous metal air batteries is that if we put it in the fire, it will not catch fire actually. Most of you know, I think the French delegate who are here in India now know at the moment the temperature is fairly cool, nice. In the May, it essentially boils. And we know what exactly happens during May. I think only after we put those vehicles on road, we know the lithium-ion batteries, we know the actual reality. We may have to really spend so much of energy cooling them during discharge and charging process. And the zinc, like I specifically talked about zinc, aluminum, and iron. The reason is that zinc in India is fairly abundant. It's probably one of the, like it's one of the largest producers of zinc. We know how to deal with zinc, and so do we know how to deal with iron. But the thing is that iron air battery is not as great as zinc air. I think the self-discharge process is fairly prominent, and I think I'll keep that aside. Whereas aluminum is very good. India is also one of the good bauxite producers. I think we have good amount of aluminum in India too. So all these 3 guys are fairly good. When you look at lithium, lithium doesn't come from India. Cobalt doesn't come from India. Nickel doesn't come from India. Manganese doesn't come from India. Almost all these guys doesn't come from India, including carbon, the graphite. So whereas the zinc, aluminum, and iron, we have in-house resources. The thing is that we know how to do the engineering and put them on board. I think with our French partners, I think we need to really go deep into the electrochemistry as well, because the France has a rich electrochemistry expertise. And I think this R-S2E is the greatest example. When I was there, it was Alisto. Now it has gone to RS2E. So I think it's one of the largest consortiums. So that electrochemistry knowledge can potentially help us how to improve these technologies and do the investment similar to the lithium-ion, so that these technologies can also take over certain portion of the energy storage market in future, if not in Europe, in countries like India and Africa. And I'll skip this part, and essentially this talks about the same thing. But I want to just quickly compare the zinc air and the lithium-ion. Sometimes there is always a misconception when you talk to people, zinc air is still far inferior. I'm just going to give you some realistic example. Here is a comparison of specific energy against various technologies. Let's look at zinc, the lithium-ion, and then the zinc air. In terms of energy, lithium-ion and zinc air are fairly comparable. Zinc are seriously comparable. But then when it comes to power, the lithium is fairly high, whereas the zinc, it can vary all the way from one end to the other end, depending on what you're working with. But most often it falls at the lower end actually. So this plot clearly kind of highlights that in terms of energy, zinc is not really that bad. But in terms of power, it's seriously bad. So that's why I've said at the beginning, it cannot go to any high power applications. It can go to 2-wheelers and 3-wheelers, which run for less than 100 kilometers a day. I think that's fairly sufficient, and they don't drive at very high speeds, probably at the 60 kilometer per hour speed. And I think that that entire electric vehicle market can be moved to the zinc air battery. And one of the things is that the stationary energy storage that Professor Ashok talked about, the wind and Anson talked about, wind is available predominantly in 4 months' time. And I want to store that energy for 4 months. How am I going to store it? Lithium-ion, any conventional or state-of-the-art battery technologies cannot do that. I think we have to literally move to this mechanically rechargeable zinc air batteries, where I store the energy in the form of zinc plates. I need it, I put it inside and run the battery. So when power is available, I regenerate them from the spent zinc to the actual zinc metal. So this technology in the Indian context is very, very prominent. And we strongly believe after our initial piloting, we'll be able to understand the realistic problems. When we implement them at the large scale, then we try to solve that and take it to the commercial reality in 5 to 10 years down the line. So I think the power-wise, I've talked about power-wise is a bad one. And in fact, the power-wise, I think fuel cell is also bad. I think it doesn't matter if you compress the hydrogen to a liquid like cryogenic system, then the power will be quite high. Otherwise, hydrogen fuel cells cannot also take over. One quick thing I also want to compare is that. So there was a nice paper from in Nature Energy. So where they have taken various vehicle sectors and they try to compare the price considering the driving range And they've taken all the way from nickel metal hydride lithium-ion down to lithium sulfur battery and the acid batteries as well. You could see that the lithium-ion, for let's say I take a vehicle of 600-kilometer range, it costs somewhere around $45,000. And you could see the zinc-air battery, which lies at the lower end of lithium-ion battery. And zinc-air batteries are not produced in mass like lithium-ion. Zinc-air batteries are produced at a very small scale. So apparently, when it goes to en masse, I think the cost of the zinc-air battery are expected to go down predominantly than the lithium-ion batteries as such. So I think there's a company, OAS, they are already selling at $160. I think the lithium-ion companies come around $200 to $250, right? So whereas here it's like just I don't know $160. And when it goes to en masse, I think it can go all the way down to $50. If we just look at this like a price drop as a function of production rate, it can go down to even $50 per kilowatt hour. And that's what India requires. India requires low-cost options. And the most important thing about zinc-air battery, one, I talked about capacity and energy density. The thing is about safety. I think the safety standards in India cannot literally follow the safety standards that's being developed in US and Europe and in Japan or any other countries. India has to develop its own safety standards because of the conditions at which we operate the vehicles. So, and the cost per kilowatt hour, there was one specific paper which says it can go all the way down to 10 USD. I think although this is going to be a very ideal number for zinc-air batteries, but I think we can go there. And zinc as a resource is at least 300 times abundant than lithium. And the other important thing is that if you go to lithium and lithium iron phosphate chemistry, then we don't talk about cobalt. I think cobalt is another significant driver. I think where India is completely going against all this Chinese businesses and moving into lithium iron phosphate business completely, so that we don't have to rely on the rare earth elements from only two countries, China and Congo. And the fabrication can be done in the ambient conditions. And technology is proven. I'll show one example. Long back, there was a company called Electric Fuels in Israel. They ran the entire bus using this mechanically rechargeable zinc-air battery. And in fact, we talked to them directly and asked them why they really did not consider take this technology forward. Their answer was very simple. At the time, lithium-ion battery funding was so high, so they jumped from zinc-air battery to the lithium-ion batteries. That's it, as simple as this. In terms of performance or the cost-wise, they were same at the time when they launched this vehicle. So these are the bunch of packs that I'm showing in here that we have developed in our laboratory, and they are in fact fully ready to go. These are one of the oldest packs. Now we have large battery packs where we can essentially pull the cassettes out, insert a new cassette in, and we also develop full-fledged battery rechargeable banks, which are powered by DC power supplies, and they can be recharged in a few hours time. So the whole process that we have developed is you can recharge the battery in less than 10 minutes, and that's something that we require also. Conventionally, swapping batteries is a good option. We can recharge them very quickly. And here we are showing one more option. We can also recharge these things much more quickly, like the battery swapping. The thing is, it's more like the Lego blocks. Once, if one of the part failed, we can just literally pull that out and throw it and insert a new part in, like the conventional, unlike the conventional electrically rechargeable parts. They have multiple advantages, and we are eagerly looking forward to execute this technology in the Indian context. Hopefully, we can also partner with our European partners, find new collaborations to understand the electrochemistry further and try to avoid the pitfalls of this technology and take them forward to the commercial reality. With that, I thank the entire team so much, and I take questions.
Thank you, Aravind. Thank you very much.
François, I think your voice isn't audible.
Silva,
No. Yes, can you hear me?
okay. Your mic is not on.
I think
my mic is on, so I should be audible. Can you hear me? So looks like my mic is okay. Aravind.
Can't hear you.
Should I just leave a text?
Yeah, you take the text.
No, I can see you.
Okay, I'll do that.
No, it's okay. Can you hear now? Is it possible?
Yeah.
Okay. Can you hear me?
Speaker is not working.
Sorry, can you hear me now? Because my mic is on, so I should be audible, or at least it's on your side, which will not be easy for the question. Okay, if the sound issue is only on Aravin's side, have we got some question from the attendees? Any question? Can you raise your hand?
And tell him that you are fine now.
Yeah. Yeah.
If
I had a question, if I can ask.
please, Professor.
I saw your first slide, beautiful slide of how India carbon dioxide emissions will grow and what we need to do each one of them. One thing on the solar when you presented some 450 gigawatt. I mean, that could be the capacity, but you really have to talk in terms of energy. I see a lot of talk in terms of power, but finally it is the energy that will matter. So why, I mean, I just thought that so comment, finally, what will have to be reduced is the energy, not the power.
That's a fantastic question, Professor. So considering just the 4 hours of full sunlight intensity we have, we need to install 450 into 6 times if you want to generate the total energy requirement. So we are talking about several gigawatts of renewable installations. I think, yeah. So I think
we should figure this out.
Exactly. Yeah. That's a fantastic question you pointed out. Yeah.
I think rest is very. Thank you.
Thank you. Okay. Again, we have gone.
No. This time it's me. This time it was me. Sorry, sorry. Don't worry. We also, if you could develop just a little more, you show some electromobility application at the end. What would be the best application for this kind of battery, in your opinion? Will it be the stationary, or will it be the EV, or is it regarding what would work the best?
Yeah, so let me just talk. I think it has application in both the technologies. Although in EVs, the standards are fairly stringent. I think this technology taking over EV will need some time. Whereas stationary energy storage, I think we really don't need to worry about the space. I think we are not constrained about the space too much. I think just put them under the building and then they're good to go. And I strongly believe the stationary energy storage, in our department, we are already installing nearly 3 kilowatt plant, 3 kilowatt hour, plant. And at research park, we have planned another 5 kilowatt hour. So these are all stationary storages, storage systems, which are going to be in use in less than 1 year's time. Whereas in the EVs, we are still trying to understand the safety protocols and no leakage and a lot of other things that we have to worry about. And only after these standards are tested on these batteries, only then they can go to the EVs. So first one will be the stationary storage. Over time, after we master the technology and make them perfect, it has a potential to go to the EVs. Even in EVs, only certain sectors can attract this battery technology. That is like two-wheelers in Indian context. No cars for sure. I think cars definitely cannot operate as zinc batteries because the power requirement is fairly high. And so do trucks. Trucks cannot operate. But the city buses, which run for a few kilometers, a few hundred kilometers a day, and the two-wheelers, which run for like at the max 100 kilometers a day, and the three-wheelers like autos that typically predominantly exist in South Asia, they can run on these battery technology.
Okay, clear. Thank you very much. Thank you. Thanks a lot for this very interesting presentation. And I'd like to invite now Professor Sylvain Franger to come and to talk about his work to us. As many of you have understood, we are in hybrid format here in Madras at the IIT Madras Research Park. So a lot of researchers are located in the same place. Sylvain?
Yeah.
The floor is yours. All good.
It's fine. Okay, so first I would like to thank the French Embassy for this wonderful organization and this seminar and the workshop. And also I would like to thank our guest in IIT Madras Research Park for hosting this session today. And my special thanks to Professor Chandran for the extraordinary tour we did this morning and the discussion fruitful we had, and hopefully we will have more discussion for sure in the next hour. So Hi to everybody. Hi to my French colleague in Paris. So I have the chance and the opportunity to be in Madras today, and it's very, very great. So I would like first to give you a glance of the research activity that is going on in my lab in Paris Saclay about energy storage and more precisely about batteries. So we are focusing on lithium-ion batteries. So on this topic, we are regarding new materials. So we had some activity in the past about lithium iron phosphate, and we did technology transfer for this compound to Trion company. So now it's on market. We also had work done on nanosilicon with the CEA in Saclay and in Grenoble. And this kind of material gives us also the opportunity to model more precisely what's happening inside the electrode during the cycling, because as you know, silicon is having some issue during lithium insertion and lithium deinsertion, for instance, because of the volumic expansion. So we had some modeling about this behavior. And then we start to model more and more the electrode behavior in the battery. So we had a project with SAFT, which is now a total company, about the porosity modeling inside the anode materials, especially graphite. And it gives us certain expertise about impedance, because this is the technique we are using to model mostly and to have access to many information inside the battery at the electrode level. If we are going with the high frequency in gigahertz, for example, we can have access to electronic transfer inside the electrode. And if we are going to lower frequency, we can also access to ion transport. So with this knowledge from electronic ionic transport issues, sometimes we can also have some good information, and we can also give this information to the manufacturer to implement in the battery electrode processing, to implement what we know about the issue that can happen inside the electrode to make better electrode with better performance. So we also had this modeling that I will present just later. I will focus on that because this is something that I think is quite interesting for many companies, especially the car manufacturer like Renault, Stellantis, and EDF also. We had a different project with this company on the modeling of battery aging, and I will focus later on that point. So we work also on micro battery. So you can see down on the left of this picture, what we are also doing. We are making new electrolytes, polymer electrolytes, new micro battery architecture in 3D to increase the battery capacity with the same surface area. So this was made through a PhD thesis in relation with ST Microelectronics. And we start also some work on all solid-state batteries, even with incorporating sodium solid-state batteries, working with both lithium and sodium. But we would like to implement beyond the lithium battery, and sodium is also something that can be interesting, as previously shown by Christelle Laberty, that sodium is less scarce than lithium on Earth. So there is already an interest to move from lithium to sodium. So we are also looking at the interfaces, the inside of the electrode, which are very complicated for solid-state battery, and also the process to make this quite reliable. So now I will move, as I said, to the battery aging modeling, because this is something we are doing with the car manufacturer, and we developed with EDF, because the awareness of the battery capacity, the battery power, the battery behavior, and the prediction of the aging of the battery is something really important, because there is a commercial concern for the manufacturer to guarantee the reliability of the system all along its lifetime. But also there is a strategic concern, as I will conclude my speech, and you will see that if we know exactly what happened during the solicitation of the battery, we can perform and avoid the more impacting phenomena. And then so this will be taken in charge by the BMS, for example. So we need to know where are these most impacting factors. So the modeling, as it has been shown by previously Samantha from Total, the modeling, there's different kind of models you can apply. So we, my team, are regarding electrochemical, thermal, and mechanical modeling. So, and then also about aging. So, as you are aware, inside the battery, there is many things. Obviously, there's many components, and each of these components can give a rise to side reactions during the life of the battery. And all these side reactions will probably degrade the performance of the overall performance of the battery upon its life. So it's also very important to have the knowledge of all these detrimental reactions occurring inside the battery at the electrode levels, but also inside the electrolyte, maybe sometime inside the membrane, and also the interplay that can also arise between all these side reactions. So one reaction occurring at the positive electrode can have also one effect at the negative electrode. So the knowledge of everything what's happening inside the battery is something that of interest to model with great accuracy and reliability what's happening really inside, and to predict the life of the battery. So this is what we are doing right now in one PhD with Stellantis company. We are modeling the battery at the electrochemistry level, so through the knowledge of all electrochemical reaction occurring inside the battery. So I will not take too much time to detail all this. As you know, there is obviously electrochemical reaction for the normal process of the battery, but there is also some diffusion issues inside the solid part, inside the liquid part, and also sometimes inside the separator. So through all this equation, we have access to different parameters. From a thermal aspect, this is also important because there is interplay between temperature, obviously, and electrochemistry. And sometimes it's going in the right direction, but sometimes temperature can also increase the side reaction. So the knowledge of the inside temperature of the battery is also something which is very important. And the temperature is not always same on each part of the battery. There can be some gradient, and we have to know where are these gradients and what is the amount, the ratio of the gradient of temperature inside the battery. So we are also modeling this. And we wanted in this PhD thesis to add the mechanical aspects, because I was saying that silicon is taking more and more importance in lithium battery, especially to enhance its capacity. So we are going slowly by slowly to remove graphite and to replace graphite by silicon because of its good capacity, but silicon is undergoing huge volumic variation upon cycling. So we have to know what impact will have this volumic variation at the electrode level, but also at the cell level. So for that, we have to know mechanically what's happening inside the battery during cycle. And all these three main, I would say, sciences, electrochemistry, thermics, and mechanics, have to be merged together and they have to be coupled, because there is some coupling effect, and this is what we are regarding right now. So I was moving about aging because, as I said, the aging process inside the battery is something of importance, and we apply a concept that has been developed in mechanics, in fact, because it's very convenient to check the aging process of a battery, because you can consider your battery as a mechanical system. You put in as an input, there is a solicitation. It will be current, for instance, for the battery, and you check the performance, which is the output. And depending on the input, the output will be different, and you can model the behavior of the battery and check upon cycling what's happening. So the main aging factor for a battery will be temperature, obviously, because, as I said previously, temperature can be good sometimes for the battery. It can enhance the redox reaction, the electrochemistry, but sometimes it can also enhance the side reaction, like the SEI formation, the passivation on the electrode. SOC is also something of importance, because SOC corresponds to the lithium content inside the electrode. So according to the lithium amount inside each electrode, the chemistry and electrochemistry of the electrode reactivity will not be same. So SOC is important. The current, as I said, because obviously the low and high current will not have the same effect on the battery and the electrode behavior. And the ampere-hour throughput, which is kind of a history of what all the materials inside the battery have seen since the battery has been made. So we choose to apply a weighted ampere throughput model, which is a model developed by mechanics. And we did different solicitation on the battery. We checked the capacity, the internal resistance of the battery after 100, 200, 500 cycle. And from that, we are checking both capacity and internal resistance on the battery. So with this approach, we were able to decouple the cycling effect from the calendar effect. As you can see down on this graph, if you start with the calendar effect, you will decrease little the capacity, and if you are just after a cycling effect, you will decrease more drastically the capacity. And if you start by cycling, so you will decrease drastically, and if you apply after cycling calendar effect, you will have a slower slope. But starting from the same point, you will reach the same points, whatever you start with, either cycling, either calendaring effect. So this is the proof that you can decouple both effects and write the formula which is written on the right, that the capacity will decrease because of two terms. One term due to the cycling aging, and it will be seen through the ampere-hour throughput seen by the battery, and one term which is in the square root of time, which is associated with the calendar aging. And what is interesting with this approach, this model, is that you can put a weight to the main aging factor I shown you previously, temperature, current, SOC, for both cycling and calendar aging. So you will have a mathematical approach of the aging and the battery with the different weight for cycling and calendar from temperature, current, density, and SOC. So after our experiment, we collect the data, and then you can see the different function, the weighted function I was telling about temperature, current, and SOC for cycling. This is the F function. And for calendar aging, this is the G function. And for each function, you will have the behavior of the importance, the impact of the parameter on the aging of the battery. And more interesting, because in our lab, we have also some physical and chemical facility, you can also check, because modeling is always good when you can cross-check with more physical and chemical information to see that what you are saying is related to something real in the battery. You can check that what happened really for the materials inside the battery, for the electrodes, the electrolytes. You can rely, you can assign all the parameters, the function, the mathematical function, which has a reality with the physicochemistry of the material. So at the positive electrode, you can rely on crystallography change about the material during cycling. You can also have some dissolution of some metal elements. Mostly manganese will dissolve preferentially and will cross the electrolyte and redeposit at the anode electrode. And at the negative side, you will have mostly passivation layer. So the SEIs, you can see above the electrode, but also inside the porosity, and you can also model the porosity and know that through this, you can have access to the main factors that will have impact on the aging of the battery. And this is related, as I said previously, to each of these weighted functions that are also related themselves to one parameter, temperature, current density, and SOC. So to conclude about this modeling, this can lead to mostly accurate prediction of the capacity of the battery upon time. So if you have different solicitation, as you can see with the different kind of driving, you can say if this battery is inside the car, for example, we can have urban driving or highway driving. So solicitation with the current density will be different. So you can input this inside the model and check that you will see the tendency that the simulation, the model will give exactly a good prediction because it goes through the experimental point. And this is very interesting because it can predict with a certain accuracy the remaining capacity after a certain time according to the solicitation you are giving to the battery. But this model can also do some optimization. You can see to the graph according to that parameter that with the knowledge of the weighted function associated to the current density and temperature, for example, that on the yellow curve, you can see that if you are charging very fast your battery, the degradation of the battery, the aging will be less if you are doing this fast charge at 40 degrees, better than if it's done at 25 degrees. So this knowledge is very interesting because it gives also some clue for the manufacturer, the EV charger companies, that if you go for fast charge, this is important to heat the battery because the degradation will be less at 40 degrees than at 25 degrees. This is only possible through kind of model that we are providing right now, and this is why it's important and interesting. So I think I finished my talk. I would just say, I don't know if there is French student listening connected today, but I would say to this student, for sure, come to India. There is amazing labs. I visited in IIT Research Park yesterday and this morning. Amazing people with lots of startup people. We are very creative, so don't hesitate. Come to India. Thank you.
Can I have a question, please?
Yes.
The question that I have is a very, very interesting, sir. I've never seen anything like this. That if you fast charge at 40 degrees centigrade, the deterioration is less than when you do it at 25 degrees centigrade. You are talking about what, 1C charging, 2C charging, or
This, it was a difference. We highlighted the difference in the degradation rate of the battery compared to C/2, so charge in 2 hours compared to 0.7 charge.
okay. And second, by and large, would you say that for almost all chemistries? All lithium-ion chemistries?
Yes, I didn't show, but here in fact, if you use this weighted factor for each parameter, if you change the battery technology, the battery chemistry, you will have exactly the same shape of curve. You will only have a difference in the value.
This is a very counterintuitive result.
Yes, yes.
We always thought that temperature will hurt charging.
No,
you
in
don't
fact,
fast charge.
Yes.
Fast charge. So
yes.
I'm amazed, and we would love to understand this more and try this out, because we have high temperature without doing anything.
Yeah, but if you see, it's really important for charging. For discharging, there is a less impact.
Yeah, that we know. That even we have figured out.
But for charging,
Fast
yes,
charging, we did never try.
it is clear, because if you see the value, it's 3 times. There is a
We
factor
will
3.
take your presentation.
I have one question. That's excellent. Like, that's again on the same area. So typically, the more the temperature we go, the SEI tend to decompose. Right? Apparently, I think when the new SEI layer forms, build up the gas inside. And since the reaction is also exothermic, we tend to, like, thermal runaway accelerates over time to keep accumulating this issue. So I'm just linearly extrapolating this. As we move to the higher temperature, the more the SEI decomposition, the more the electrolyte chemistry will form the new SEI. So is there any fundamental reason why charging at high temperature helps retaining the capacity? How about the safety in the long run?
Probably it's linked with the fact that you will also increase the diffusion of the lithium ions.
Okay.
And then you will not create too much lithium concentration gradients. So you will avoid lithium blading on one side. You will allow all the lithium to go inside, deep inside the electrodes faster. So probably it's linked to this. Probably it will also be dependent on the full chemistry of the battery, because if you have silicon on one side, probably there will be some little changes. Here it was with graphite on one side and NMC or LFP, but it was always graphite as an anode. So we have to check what's happening if silicon is used as a negative.
In our lab, what we have done is we literally explored a handful of batteries inside accelerating rate capacity. We literally tried to do the fast charging and the slow charging. One common trend we have observed is that the faster we charge for like 1,000 cycles, the temperature at which thermal runaway accelerates happens is at very low temperature. So, and the same thing we observed when the charging happens at slightly elevated temperatures. Although I didn't look specifically at the difference between 20 and 40 degrees Celsius, we charged at around 60 degrees Celsius, and then we observed that when we consistently keep doing it, thermal runaway actually.
If you see the tendency, if the temperature is too much, because after 50, we reach until 60. After, there is also a very strong degradation. So the temperature should not be too high, but 40 is better than 25. Okay. This is true.
I think this is
no, gentlemen, if I can, we're having also a question from Christelle, and maybe you could interact a little later here locally at Madras. Christelle.
Yes, so thank you, Steven, for the presentation. So you said how important is it, the mechanics inside the battery?
Yeah.
What type of inputs do you need for modeling mechanics in batteries?
So in fact, you need the many things. You need to know the parameters, the intrinsic parameters of the different materials, so like plasticity, elasticity, Young modulus, things like that. And then after you have to model this, to put this inside the software, like a console, for example, we are using. And then you will have when you will put current will be seen as a strain for the mechanics point of view. And because of this strain, you will model, you will simulate the behavior of the different materials. And if the overall battery is increasing in size and where it will increase more.
Okay. Okay.
Thank you very much.
For all these things, mechanical, thermal, and electrochemical modeling, as you can see here, through the equation, you need many parameters. So you have to do experiments on one side to provide this parameter to implement inside your model.
Thank you. Thank you very much, Sylvain. We've got time for one last question. We're running something like 40 minutes late. So what I will do, I will put my email address in the chat box before the end. And if you want to get in touch with any of the speaker, please just let me know and I will connect you. I can't give the email address of everybody, but I will share mine with you. And no worries, so you can directly get in touch. I would like to invite Miss Sandhya to come for the next presentation. Great. Okay, Sandhya, over to you.
Yeah, good evening. And so our topic today is battery and charger. And pretty much, this is something that we do every day at our Center for Battery Engineering here at IIT Madras Research Park. And I'm joined by my colleague, Ms. Dr. Bharati. And so we know battery and chargers are very important in the EV subsystem ecosystem. And why EVs are very important for India. I mean, we saw how the pollution and the greenhouse gases are going to have a major impact on how the world is going to be impacted by the climate change. And our nation also has a commitment to reduce the emission intensity by 45% by 2030, which is very aggressive. Earlier it was 35%. And now it is, our Prime Minister has increased it to 45%. And there is also a commitment towards net zero greenhouse emission. And but, for EVs to become successful in India, the market, we are a developing country. So cost is going to be the key factor, affordability. So we want low cost with a very high quality. And, the Indian road conditions and our temperatures are very different from countries, so we cannot adopt the designs that have been used in other countries. We are having our own designs and lower maintenance costs, which is very important. And EVs, because there are very less moving parts, the maintenance cost is going to be 50%. And so the cost of ownership over a period of time is definitely going to be much better than the conventional vehicles. And the EV drivetrain, the motors, controllers, batteries, the charging chargers, all of them have to be at low cost. We have to compete with Chinese prices, but with European quality. And so for the lithium-ion batteries are the most common ones. We saw, and there are still a lot of research going on how the chemistries can be improved, how the energy densities can be enhanced. So what we have looked at are NMC and LFP lithium chemistries for our batteries. And the most important thing for batteries, the best performance for a battery starts from the choice of cells, which requires cell characterization and testing. And we have today morning also we had a presentation on how we do the characterization here and choose the cells. And after that comes good mechanical thermal design to make sure that the battery pack is giving us the maximum life for the Indian road conditions and temperature. So we do the cell characterization, look at the capacity degradation over the different cycles that the battery goes through, and the thermal designs, where we study how the cells they are impacted by the rate of charge or discharge, and how the heat has to be dissipated to protect the life of the cell, and the mechanical design, how the battery packs are going to be impacted, adapt to the Indian road conditions, and the cells should not get bulged. And then of course the electrical design. So the key here is to protect, while we take care of all these things, the thermal and mechanical design, the key, another most important component is going to be the battery management system, which ensures the safety of the battery, or it's the protection mechanism for the battery. And the software takes care of proper charging and discharging, make sure that the cell temperatures don't go above the over temperatures or under temperature, over voltage, under voltage. All these parameters need to be looked at, and if there is a critical condition crossing thresholds, it should make sure that the battery is protected, it shuts down and takes care of recovery things. And another important thing that the battery management should do and does is the cell balancing. So you make sure that the cell voltages are even across the battery pack, so that when you're charging and discharging, all the cells behave uniformly. And for this, we need to have constant collection of the data while the battery is in operation, and also under idle conditions, to see where these parameters are getting impacted. And this will also help us in predicting the life of the battery or the degradation of the battery, so the users can make sure that they are taking precautionary measures or conditions for protecting the battery. So at CB, we have developed our own, designed and developed our own two-wheeler, three-wheeler batteries, 48 volt, 60 volts, 72 volts, and with varying capacities from 0.7 small ones as 0.7 kilowatt to 8 kilowatt. And these are technologies that have been already transferred to companies like Signy, Kinetic Green, and SVT. And on cars also, we have developed a 72 volt, 11 kilowatt battery, and technology has been transferred. And bus and storage is another area that our batteries, we have developed batteries from 380 volts to 750 volts capacity, 110 kilowatt, and the next ones that we are working on is the 1 megawatt and above. The next item on our EV subsystem is the chargers, and these are the key functions for the charger is to charge the EV battery. They typically take supply from the AC supply from the grid and convert it to DC and charge the battery. And at the same time, as we looked at, the charging process also has to be controlled, and it cannot be a complete push of large current, high current into the battery, which will damage. So that also has to be a gradual process of charging. And so for this, it has to monitor the voltage, current, and temperature to protect the battery. So the key features of a charger would be the constant current, constant voltage profiling. Basically, when you start to charge with the constant current, and then as the capacity reaches almost the top, then the charger gets into the constant voltage mode. And the built-in protection and the intelligent charging, again, the smart chargers, the metering, because this is for a business perspective, you need to know how much current is being used and how much charge is taken into the battery. And for this, we have a smart platform connectivity where all this data is collected and charging is done. So the chargers that we have are portable chargers for the small vehicles, two-wheelers, autos, and three-wheelers. So 48 volt and 60 volt. And we also have these bulk chargers where there is an energy operator and they supply a lot of batteries to their customers. And when they come back for charging, we have this say 8 slot chargers, 16 slot chargers. It's a modular design, it can be extended. And we have a lock smart protocol, VBCC, LS VBCC protocol, where the charger, vehicle, and the battery exchange information. Basically, the data logged during in the battery is collected through the charger during the charging cycle, and which is used for backend analysis, data analytics. And we have these AC chargers that for 3.3 kilowatt up to 22 kilowatt, and the DC fast chargers with different Chinese, Japanese, and European Bharat standards. So the next interesting thing that we are looking at is the bidirectional charging. So now we have these batteries charged in the vehicle, and when they are not in use, when there is excess, the batteries power is there in the battery, how do you take it back to the grid when there is a shortage in the grid, or to shave your peak current usage? So this is kind of a reverse charging or bidirectional charging. It helps to supply energy to the grid during the peak hours. So one experiment that we are doing in IIT Research Park is, let's say we have a 3 kilowatt bidirectional charger with the CCS protocol, and we have these solar panels. So during daytime, we have a vehicle and the battery, or it's a typical a small pickup truck, which is a 10 kilowatt motor that we are designing right now, and with a 350 volt battery pack. So during daytime, this mini truck can be charged with our charger, and later in the evening, when it goes back and gets parked at the let's say in the campus, so the excess power in the battery, the charge in the battery can be fed back to the home to power the home, or if not needed there also, it can go back to the grid. So this is an experiment that we have started, and this is going to give us a lot of insights in how this whole thing can be replicated at larger scales. So we have done a lot of work on the analytics and the management side. So lot of data that we have collected while the battery is being used in the vehicle during charging and discharging. And so there are solutions that we have for charging infrastructure and the fleet management. So basically a fleet operator can look at the battery data that is used in all the cars or the vehicles. And so when a driver needs a battery, which is the nearest charging location, and how much charge is left in the vehicle, and or the battery health, which requires a replacement. So these we have designed this solutions, and this has been also technology has been transferred. So that's in short what we wanted to talk about. Any questions?
Thank you very much, Sandhya. Have we got some questions from our colleagues and from the audience? I've received some of them. Can you raise your hand if you have one? I have one question regarding the normalization of the charger in India. Is there any can you just explain us the landscape of the charger types in India? Is there any standardization, normalization?
So we have the, we have an understand charger, that is our Indian standard that we have.
So can I answer this question, because this is so India has not evolved a charger standard. By and large, though, we follow European standard CCS. There is a lot of pulls and pushes, primarily from the Japanese. They want to push Chandran. I think by and large, we are very close to CCS, but India has not. I mean, I was chairman of a committee to decide on charger. In a very short time, we were able to do some minimum standardization. After that, government is messing it around. But by and large, CCS is fine.
Okay, thank you. Another question we received regarding the potential difference between fixed battery and swapping battery, and any difference in the technology which is used for the thermal management and mechanical side of these two types?
No, it is the same. It's just the the protocols and the battery management software that is going to make the difference between a fixed battery and the swappable battery.
Another thing which comes in is that our battery is ergonomic. How much weight can one person take, or if there is excess weight, then do we need a mechanized solution to pull the battery from the vehicle or from the car?
Okay. There was one question also on how much energy is taken from the pickup, is lost from the pickup of the battery. Example, when the battery is fully discharged, can it be an issue so it can't be used by the user?
Sorry, how much? Can you repeat that question?
We can take lots up to a second for each battery, but since there is a lot of data points, so we try to take every 10 seconds, every 30 seconds, based upon the parameters of the battery.
The data log you mentioned, is that the question?
Sorry, yeah, it was, I couldn't understand. Yes, please.
Can you please repeat your question?
Question we had was regarding, say, how much energy is taken from the pickup of the battery, because in the case the battery is fully discharged, the battery will not be usable in the morning.
Yes, so if there is an excess, the battery's SOC is above certain level, only it can feed back to the grid. Otherwise, it won't. It will only.
Okay.
There is some certain voltage.
Yeah, that's SOC. SOC percentage, above a particular SOC percentage, only it can discharge.
Okay. I think we will move forward because we're still running late, but it's quite interesting. Let's go with the next speaker. So thank you, Sandhya, again. And would like to invite Mr. Milind Kulkarni to show his presentation.
I want to just say that Milind is going to lead major solar cell manufacturing effort in the country. So we are very proud to have him.
Okay. Milind, the floor is yours.
Right. So can you see my screen?
Yes.
Yes. Yes, please.
Okay. Thank you for inviting me to give this presentation here. I just want to clarify that my affiliation has changed this week. So I have taken over as the president of PV manufacturing, Reliance New Energy Solar. Just started my work 2 days ago. So just wanted to clarify that my old affiliation is no longer valid. So this is a very short presentation. In the interest of time, I'm briefly going to discuss present solar value chains. And then I would like to spend some time on what are the emerging technologies of interest. There is a lot happening in this field, but I will filter all the technologies and discuss only a couple that are of interest. And in the end, at the national level, what are the choices available to India, for that matter to any country right now that wants to really do something big in solar manufacturing. What are the present choices available, and how to carve out a path for the future? Because this sector is evolving, and it is very important for anybody who is participating in this sector to understand the roadmap and be ready to adopt and accept the changes. So that is basically the scope of this presentation. Here I have shown you the most dominant value chain to make solar modules today. That offers the lowest LCOE, that is a levelized cost of energy. The process starts with making polysilicon. And here I have shown you the production of polysilicon by a highly differentiated fluidized bed reactor technology. And what you see in the bottom, I don't know if you can see my cursor. What you see in the bottom is essentially the actual polysilicon produced by fluidized bed reactor. And the size of each granule here varies from 0.8 to 1 millimeter in diameter. The next step is to melt this polysilicon in crystal growth furnaces and grow single crystals by Zakralowski process. There are two options here. One is either grow crystals in a batch or semi-batch mode, or grow them in a continuous mode, in which process you continuously melt fresh polysilicon at the same rate you are growing crystal. So that would be a continuous process, and there are certain advantages to doing both. A crystal grown in this fashion is shaped into bricks, and these bricks then yield various wafers of desired thickness in wire saw. Today, diamond coated wire saw process has become the industry standard, and the thickness of wafers today, depending on the format, varies between 165 microns to 180 microns. Now, these single crystal cells are then used in making single crystal based solar cells. Today, the workhorse, the most popular solar cell is PERC, and the emerging technologies are TOPCon and heterojunction. We will actually talk about that. And module assembly is essentially actually a relatively simple process. One activity that is happening here is to ensure that modules need to be bifacial, and the packing density of cells increases such that the module efficiency also increases. So this is essentially the present value chain that is dominating. It has around 85% market share today. Okay. Now, the past value chain, which was dominating just three to 4 years ago, but that is losing market share, looks very similar to what I discussed, except that the crystal growth is based on casting here. And in this process, cost of crystal growth itself is like very low. But casting produces multicrystal, which has various defects, because of which the efficiency of cells that can be produced is significantly lower, anywhere from 2% to 1.5% absolute. And that really results in a significant increase in LCOE. So because of that, this value chain is not popular anymore, and over a period of time, one can expect this value chain to essentially taper off. Right now, the market share is barely around 15%. Okay. So now let us look at what is happening in the emerging value chain. Without going into details, if you looked at previous value chains carefully, there are various steps from producing silicon containing gases, then from that actually producing polysilicon, melting polysilicon, then growing single crystal, and then shaping and slicing it. In the slicing process, around 40% of silicon is lost as curve because wafers need to be cut with the diamond wires, diamond coated wires. If we can eliminate some of these steps, that is extremely attractive from value proposition. So one of the promising technologies, and there are various groups working on it, is what I like to term as the direct mono wafer technology, or DW mono. In this process, instead of making polysilicon from TCS, which is one of the silicon containing gases, directly single crystal wafers can be produced on a single crystal base. but it involves certain tricks. After we make wafers, which is shown by the gray block here, the base will have to be recycled. And for that purpose, there has to be separation of a produced wafer from the base. And most popular method to do this layer separation is by anodic etching and subsequent heat cycles. I will not go into details of that. And for this technology to be successful, the number of recycles we are talking about actually should approach 50. Otherwise, it is not going to be cost effective. And it does eliminate 50% of polysilicon production. The entire traditional crystal growth process, which involves melting of polysilicon and growth of crystal and entire slicing operation, where significant kerf loss happens. So it has significant advantages, but direct chemical vapor deposition to make single crystal wafer itself is quite expensive, both from capex point of view, from operational point of view, and a recycle of substrate is absolutely required. And the quality of product in theory can be close to that of Zakrzewski process, but in practice it has not been demonstrated so far. But what has been demonstrated is that it is possible to make high efficiency solar wafers using heterojunction technology, using PERC technology. It is possible to make high efficiency wafers. So that is the technology of promise in future. But it is very important to note that the present value chain itself has a significant room for improvement. So the goalpost is continuously shifting in the solar space when we talk about cost and LCOE. So it is very important to ensure that the rate of development is also is what is required and right LCOE is achieved. But definitely this is one technology to watch out for. Now there is another technology in terms of cost of crystal production is attractive, but it does suffer from low efficiency. This is what I call direct multi-wafer technology. In this process, you have to produce polysilicon, but instead of growing multi-crystal directly and then slicing it, wafers are directly cast from the melt. So it does eliminate traditional crystal growth and it does eliminate kerf loss. But polysilicon actually prices have significantly come down. I'm not talking about right now. Right now, obviously, they're selling like gold. But at a steady state, polysilicon should be selling at around $8 to $9 per kg. So the reduction in polysilicon itself doesn't add to significant cost saving. But in any case, this is a technology that produces a material very similar to high performance multi. So there has to be actually some effort to improve efficiency. Unless that happens, it is quite difficult for this technology to compete with the direct mono wafer technology, and for that matter, with the existing single crystal technology. These are the technologies that are upcoming from poly to wafers space. And in terms of cells, I would just like to actually briefly discuss one exciting area, which is essentially perovskites. Not just perovskites, perovskite silicon tandems. Perovskites are essentially organic halides. They have a structure like ABX3, and you can manipulate their ability to absorb solar spectrum. So essentially, it is transparent, and we can make tandems by placing perovskites on the top of normal silicon cell. And tandems can have various configurations. And part of the solar spectrum that is not absorbed by silicon can be absorbed by perovskite. And the tandem structures can theoretically actually yield more than 33% efficiency. And already in the lab, 31% efficiencies have been reported. Obviously, significant development is required in this area. And although there are many aggressive projections, I think this technology is of the 5 to 10 year horizon, especially when we talk about acceptable high volume manufacturing performance. With all the changes that I just discussed, if we add perovskite, and obviously it is going to completely actually change the game. And it is not necessary for perovskite silicon tandems to be successful for solar energy to be a viable alternative. The present value chain itself can actually get us to where we want. But most definitely, perovskite silicon tandems are going to act as a catalyst for improved energy harvesting, and it will accelerate all the changes that we want to see. So with this, I just want to actually summarize, show you last 2 slides. What are the technology options available today if one has to make decision? For polysilicon production, there is a Siemens process, and then there is a superior fluidized bed reactor process. But there are various, 2 fluidized bed reactor processes, only one of them today can make electronic grade polysilicon, but it is not readily available actually for India, for that matter, to anybody outside one company right now. But the Siemens process is a standard process, and it consumes significant amount of energy, but it is readily available. The technology risk is very low for anybody who wants to move into this space. For crystal growth, obviously, all the players have moved to single crystal Zakrzewski growth. The present state of the art is recharged Zakrzewski. And as I shared with you, it will evolve very slowly into continuous Zakrzewski. That will have a significant quality advantage, not just cost advantage. At least around $2 per kg cost advantage is going to be there for continuous process. And this allows crystal to grow at a single dopant concentration, and resistivity variation is going to be quite minimal. And that is a significant advantage for cell production. Now, as far as the slicing is concerned, the old standard was so-called slurry slicing, where silicon carbide particles in glycol actually slurry were doing the cutting action. But today, essentially, entire industry has moved to diamond-coated wire slicing, which has been a standard in other industries, but today it has become a standard in the solar industry. There isn't much differentiation here, but essentially diamond-coated wire slicing is the state of the art, and anybody who wants to enter into this field will have to adopt it. As far as cells are concerned, space is a little bit open. PERC today is the workhorse, and it offers very attractive LCOE. And there is an evolutionary technology beyond PERC, which is based on backside passivation, additional backside passivation, using amorphous silicon, silicon dioxide, and then actually amorphous silicon. And it works on the basis of actually tunneling on the backside. That can actually take us to around 24.5% efficiency. Now, heterojunction has been a technology of tomorrow for many, many years. Quite a few issues associated with the heterojunction are also being addressed. That can actually provide in high volume manufacturing around 0.5 to 1% efficiency higher than TOPCon. So these 2 technologies are emerging, and they are around the corner. For modules, anyway, things are changing extremely fast. Any technology change in modules cannot last for more than 2 to 6 months for any player. And what we will see is that actually density of cells is going to continue to increase. Modules are going to be bifacial, and glass-on-glass modules are going to emerge. And the gap between cell efficiency and module efficiency is going to continuously decrease. That is absolutely required for reduction in LCOE. So with this, if you ask the question, what should a country do, or what should a big company do that is entering this sector? The present options available for polysilicon are Siemens. For crystal growth, it has to be recharged Zakrzewski. And for slicing, it is diamond-coated wire. And cells, if you really don't want to take any risks, it is PERC. If you want to take risk, you can immediately try either TOPCon or heterojunction. And for modules, anyway, the equipment is standard, and one can easily actually set up a module assembly line without any problem. In the midterm, there are various options. There is one version of FBR technology that is available. If organic technology team is very strong, perhaps this technology can be purchased, and then the quality of polysilicon produced by this platform can be improved. It will take around 3 years of development. Over the long term, there are various fluidized bed reactor variants. And as I mentioned, one fluidized bed reactor technology that can make electronic grade polysilicon works today, but it may not be available for licensing. I don't want to discuss a lot more than this right now in this meeting. For crystal growth, anyway, development of actually continuous Zakrzewski for midterm will automatically happen from recharged Zakrzewski process. And as we discussed, over the long term, direct mono wafer can replace continuous Zakrzewski and even part of the polysilicon production. And continuous Zakrzewski development can be internal if right core competencies are built. Without that, it is going to be quite difficult. For slicing, once again, it is the same story. Diamond coated wire slicing has become industry standard. If direct wafer technology becomes successful, and obviously it is going to replace crystal growth as well as slicing. So in the long term, that should be carefully looked at. As far as cells are concerned, PERC is the standard, but the TOPCon is emerging because it is evolutionary, and heterojunction is going neck to neck right now by addressing most of the yield issues actually that were plaguing this sector for a long period of time. And over a very long period of time, very long horizon, I'm talking about 5 to 10 years, perovskite silicon tandems are actually something industry has to look at very, very carefully. And for modules, even in the midterm, I would say right now bifacial glass-on-glass modules are coming. Anyway, in the USA, really everybody wants bifacial glass-on-glass already. And one thing I did not mention, because it is happening in the orthogonal dimension, is increase in the wafer format. Many years ago, it was very difficult to increase the wafer size from 156 millimeters. Then slowly it reached 158.75. Now 166 millimeter, which is called M6, is the standard. And most definitely M10 format with the 182 millimeter side length is emerging. And next year it is going to be one of the dominant products. And M12 is a 210 millimeter product, which requires growth of 300 millimeter crystal, will also eventually emerge, and module production will have to accommodate that. And it is true for cells also. In fact, all the new factories that are being built are M10 and M12 compatible. And there is going to be continuous optimization in modules. So at a very high level, these are the choices available. But in the end, there is execution and then understanding of the details that is absolutely required for success here. So for example, if somebody has fluidized bed reactor factory that is available, hypothetically, you want to figure out how to run profitably will take 4 to 5 years. So it requires both experience as well as actually right core competencies to make this successful. So any country or any industry sector will have to focus on developing right core competencies with these technologies, because strategically what needs to be done has become relatively clearer today compared to 5 years ago. But execution of that and success over a long period of time involves risk. And success over the long period of time in this technology sector is possible not just by choosing the right platform, by ensuring that the capabilities of these platforms are pushed. I'm talking about engineering improvement, which are going to make significant difference. And right core competencies are built to compete with benchmark competition. So that is what is required for success in this sector for any new country or any new big company that is entering into this field. With this, I end my presentation and I'll be happy to answer any questions.
Thank you very much, sir. I'd like to first ask the participants on the call, if you have any questions, please do raise your hand. If not, we have received a few questions.
Can I ask a question? This is Ashish Garg from IIT Kanpur.
Sure, Professor Ashish, please go ahead.
So I have a question, Mr. Kulkarni, related to this direct mono wafer technology. So what do you see, how attractive this technology in terms of purity of crystals, in terms of cost, and what is its long-term roadmap? Can you comment on that?
Right. I mean, certain things I cannot actually share completely because of confidentiality, but right. I can tell you there is risk that everybody knows. And two risks associated with this are, as you mentioned, the quality of the material that you make. It is not that it is not single crystal. but it does have impurities. And it is not of the same quality as Zachralowski, but it is far superior to standard multi. And the second thing is really how many recycles will you achieve of your substrate. And this process involves anodic etching, manipulation of pores that are created in anodic etching, then creating a layer for separation by proper heat treatment. And these things can be done. The question is how consistently can you do it and what is the yield? I mean, achieving around 60 to 70% yield is, I mean, it has close to zero risk by this technology, but that is not enough. Your yield will have to be around 93 to 95% for this technology to be commercially viable. So there are engineering challenges. So it is not technology that is ready, but as far as testing the material to see how it performs with various cell architectures, that can be done. It has been done. And without mentioning names, there are multiple groups working on this. There are at least 3 groups. At least one group in the past has demonstrated that it can really show the similar, if I don't want to say same, similar performance as the Zachralowski crystal for certain cell architectures. So long story short, there is an upside, but upside is not as big as many people would think. I mean, if you do the cost analysis, maybe perhaps around 1 cent per watt compared to the standard process. It is not a small advantage. 1 cent per watt is significant, but that with significant actually risk is where this technology stands.
Thank you.
Thank you, Professor Ashish Garg. Any other questions we have from the group here? Please do raise your hand. If not, the one question that we received was, since cost estimates for reduction of solar has far exceeded most prior estimates, what are sort of future projections in terms of cost reduction in solar?
No, I can tell you now, LCOE has actually various other components right now, and that is what needs to be looked at. And it also, for the same technology, it varies from region to region, right? So from module point of view, today, really good integrated producer, if you eliminate all the margins, can make in China. Let us actually compare China now, actually, which has mature sector here. They can make mono modules at around 19 to 20 cents. Some of them can make 19 at 19 cents per watt. And when everything is under normal conditions, they can sell PERC modules at around 22 cents or 23 cents maximum, okay, per watt. That is the total cost. Now, that total cost can go down to around 16 cents. Without these new technologies, a continuous improvement in a single crystal technology that I described on my first slide can actually take it to 16 cents, and cash cost can go down to as low as 14 cents. That is significant. 1 cent per watt is $10 million per gigawatt. Okay, and at 10% discount rate, if you really take a very long term, it is $100 million in NPV. So it is. That's why I said 1 cent is not negligible. So it is quite significant. I mean, that's why I'm saying when we talk about these new technologies, I've been in this sector for such a long period of time. Even the right technology will not be attractive enough if timing is not right. Because performance curve is improving for the existing technology. Cost curve is actually improving. Everything is improving. So to make the case that somebody has to invest in a completely new technology, advantage will have to be huge. When a new technology development starts, perhaps that advantage is huge. And as you mentioned, you correctly saw the history. Everything has been improving so dramatically. Each and every expert, including me, have been proven wrong in terms of how fast this cost curve actually would come down. It's quite amazing. As a technologist, I would always continue to look for completely new technologies, but we should never take our eye off what the present value chain can do.
Absolutely. Great. Thank you so much, Dr. Milind Kulkarni. I think in the interest of time, we'll stop here. But thank you so much for your sharing your thoughts, and we look forward to working together with you.
Okay. Thank you. Thanks, everybody.
Great. And for our final presentation, we will have Mr. Anuvrat Joshi. Anuvrat Joshi is from Cleantech Solar. I invite Anuvrat to take over and share us his thoughts on what is happening on his front from Cleantech Solar. Over to you, Anuvrat.
Thank you very much, Sandhya. Just wanted to first of all, thank you, the organizers, and everyone else with just for giving us this opportunity to speak with such an esteemed gathering that we have here. So absolutely a pleasure. We represent obviously the other end of the spectrum. I've been hearing some of the very interesting developments on that the various scientists and professors and others have presented on the technical front. We obviously represent the commercial side of things, and I believe it is my mandate to sort of give a high-level picture of essentially where solar stands in India, and in particular, what is the area in which we have kind of made made the most strides. Is that a fair way to put it, Anson?
Yes, absolutely.
Yep.
If you have some slides to share, or
yeah, so we do, and I had just in interest of to be safe, I had shared it with your team. I can do the sharing as well. I just wanted to be sure that So if you guys can go ahead, please share it, and otherwise I will do the same.
I think it would be best if you share it. That way you have control of the.
Okay, I will do so. Is everyone able to see the slide?
Yes, looks good.
All right, excellent. So, so good evening, everyone. Just by way of quick introduction, we are a company called Cleantech Solar. Cleantech Solar is a Singapore-based company. About 75 to 80% of our business is in India, and about 6 or so Southeast Asian countries make up the rest of our business. Our focus has been Southeast Asia from day one, and over a period, and I should mention, our focus has almost entirely been B2B solar, which is also goes by the name of CNI solar. In other words, we as a private company try to focus not on large government contracts, but instead on providing the large industrial houses with solar solutions, be they rooftop, open access, or any other kind. I mean, and I'll get into that. That's what we do. We are roughly about 600 megawatts is our portfolio size now, which for the CNI space, if you consider the typical rooftop project size and then increasingly now open access, is a fairly big number. So, that does make us the largest in Asia largest in India and Southeast Asia with respect to CNI solar. Of course, we don't, of course, there are players in China and elsewhere who are kind of, who are potentially bigger, but, I'm referring to the rest of Asia. So with that, I think, let me go to the next slide. I mean, all of you are experts on solar, and a lot of this will be very, very basic, and I sort of, fully sort of understand that, appreciate that. I've sort of had the pleasure and the benefit of a technical training, so I was following along some of the very interesting presentations, and obviously those refer to much more cutting edge stuff. But I believe, like I said, our mandate here, at least as presented by Professor Jhunjhunwala and and Anson, is to give the picture of how things are panning out in India, in particular in the context of commercial and industrial solar. Solar is broadly divided into into three categories: residential solar, commercial and industrial solar, and utility scale solar. The better term for them perhaps is residential solar, B2B solar, and B2G solar, where the large scale utility projects are done for the government, for government discoms, and the medium term size utility scale projects are now done for open access industrial customers. And then of course there is rooftop, which are like slightly smaller than that. And residential is a whole category of its own, involving very, very small kind of projects. To give you a sense of the scale, a typical rooftop project on residential side is a 10 kilowatt peak project. A typical rooftop industrial project is a 1 megawatt size project, though we have some on as large as 20 megawatts on a single location. To get a sense of it, we are talking about a customer who has 50 acres of roofs. So, not to be underestimated, but the typical size of a rooftop commercial or industrial solar project is a megawatt. Commercial and industrial solar also has now a new category, which is solar power provided from off-site, not on-site, that is through the grid. And these projects typically are in the size of 10 to 50 megawatt for that particular customer, solely feeding to them using the grid, but directly meant for offtake by that particular customer. And many of our customers have both. And this, if you ask me which has been the hottest sector in India in the last perhaps 5 to 7 years, I would perhaps point to to B2B or commercial and industrial solar, more so than B2G or the large utility scale solar, because that grew in size and stature from around 2008 to 2015, and from 2015 onwards, while of course utility scale solar was adding gigawatts, it is the previously unknown category of commercial and industrial solar that completely took off from essentially a zero to to what's perhaps a 5 gigawatt overall industry size right now, with a potential of about probably 30 to 40 gigawatts. So that's a pretty big market, and it's a fair degree of success that's already happened in that market. Yeah, so I think behind the success, I think the most fundamental driver isn't just the reduction of costs. I mean, we did have a pretty unique point of time in India and in few other nations, but in particular in India around 2015, where solar, admittedly an intermittent source, became cheaper than the grid. So if you put a solar project on the roof, it became cheaper by more than 10%, so meaningfully cheaper than the grid supplied power. That happened around the 2014-15 timeframe. And that immediately turned the attention of the customers who were struggling with trying to meet their sustainability goals, trying to change their power mix to more renewable, to making the switch because it became at least commercially viable and beneficial to do so. Of course, as I think Dr. Milland earlier was saying, of course, and others were saying, that it is sort of the solar prices have gone from strength to strength since, as in LCOE has dropped lower and lower, which of course has made the sector even more appealing. But the big thing driving, so that was what caused it to start, and it's in a few countries, because always when you put it on the rooftop, the cost was higher than the grid and it was never appealing. That was one big factor. The other is that players like us were able to do or put together the kind of funds needed to do an OpEx kind of offering, wherein where the customer does not have to pay for the project upfront. It is us who own the asset, I mean, who sort of design the asset, plan the asset, build the asset, own the asset, and supply power from their roof for let's say 15, 20, or 25 years under a power purchase agreement. So that's sort of, I think those two together is what completely, kicked the sector into a different category. And I misspoke earlier. The sector size would probably be closer to 10 gigawatts right now, not 5. So yeah, that's where we are. So moving on to, I mean, I'll not get into too much details here, other than, and again, my apologies if all of you are extremely familiar with these topics, but, we're just trying to hit some sort of a common minimum for all kinds of different, different attendees to get at least something out of the presentation. So I'll just take a few minutes to point at some of the key factors of what is on-site, what is off-site. So on-site is obviously can be rooftop, can be ground mount, but it tends to be within the premises of the customer. So obviously, a certain degree of land issues don't arise. These projects are quick to execute. Far fewer permits are needed from regulators and so on and so forth. So this tends to go fast. The limitation here, of course, is size, right? That you can't go very, very big. At most, you'll replace 10, 20, maybe 30% of the power requirement of the customer, especially if you're talking about industrial customers. The next category is off-site solar solutions, where, of course, you can pretty much build as big a project as you wish. And the limitation here is pretty much the connected load of the customer, because across India and probably other countries, for most part other countries as well, the total connected load of the customer is what the regulations limit the size of the solar project to. Now, I don't have to tell this audience that obviously a 20 megawatt solar project effectively produces energy worth a 3.5, 4 megawatt solar project, right? 3.5, 4 megawatt coal or gas fired plant. But because of the fact that during some parts of the day, it produces almost close to 20, and during some part of the year and some part of the day, it does do that. Therefore, the regulators have overall taken a view that a person's off-site project will be limited to that size. So that's kind of the constraint, if you will, but really this is the way through which people are supplying probably 50, 60 and higher % of their, when I say people, I'm referring to industrial customers, are supplying 50, 60% of their power usage through solar. So, I mean, some of you, I'm sure, are surprised by that number, because you think of solar in its nascent stage and it's a small percentage of India's power usage. But the industrial consumers, because of the huge price benefits, I mean, they're almost saving 50% versus the grid. I mean, the grids are typically 7 rupees per watt, 7 rupees per kilowatt hour, whereas solar, as delivered or from rooftop, is around 4 to 4.5 total. Yeah, and then of course the third category is B2G, which is, everybody knows about it. It's been going on for multiple years. I mean, in India, United States, anywhere else, that's where the DISCOM buys power. There are no limits whatsoever, and the only disadvantage of that, some to a degree, is some of the inefficiencies of DISCOM remain when you take that path. But it has a place of its own, and B2B solar has a place of its own, and similarly residential has a place of its own. That said, so I think we will leave this particular slide more to the Q&A session, because there's many of the points that I've kind of spoken to at a high level, but it's just useful to perhaps note that C&I segment represents close to 50% of the power consumed in the power that is consumed in the country. I mean, maybe a little less than that, but yeah, in around that ballpark. So that is a very significant sector to address, and all of that has gotten addressed in less than 7 years period of time, which is so it's really this is the revolution. This is what's happening right now with respect to something new, and of course B2G, large utility scale solar, is in parallel going from strength to strength, in India, as you are, most of you, I'm sure, are aware. I mean, this is the sort of, obligatory commercial slide, as in just to give you a little sense of what are we talking about. So we, for example, we have developed a close to 150 megawatt project in Tamil Nadu, from which we supply a few key customers. The customers are sort of mentioned here. Each customer saves about 3 rupees per unit. It takes about 600 acres of land to be acquired, which as we have acquired. It actually has a 220 kV line. So I mean, many people don't think of solar in terms of like the real power, but this is very real power. It's a 220 kV line that eventually takes this from the entire solar park into the substation. And like I was saying earlier, the discount with versus the grid is almost a 40-45% kind of number. So meaningful for people. Everyone, most of these customers have pretty much signed up for close to the connected load, everything that the regulators would permit, and are at this point therefore replacing in some cases as much as 50%, but in all cases not just a 10% or 20% of their power, something fairly significant. I mean, and I guess next slide is just a specific example of a rooftop project. This particular project, the reason I'm sort of sharing this point, we have shared this with you, is because in a rooftop is not that small as you would think. Industrial rooftop, this project, and with some extensions, etc., is like well north of 10 megawatts. Again, this saves, it's a bit of a dated project, so therefore it saves about 3 rupees today. If you were to do this, it will probably save a bit more. But the point is that a rooftop too, in the case of this project, can offer a 10 megawatt opportunity for the customer and us to save money. Our largest project on the rooftop is about 18 megawatts, which is the customer I was referring to, with a 50 acres of roof. So I think that's everything from.
I have a couple of questions. Can I try and ask?
Please go ahead. Yeah, I'm done with the presentation.
I have two questions. First question is, much of what you are doing is under the group captive or doing it for a specific company. Do you see going forward policy coming in the way of doing it? That's a question number one. Second, India seems to have done fairly well for large solar projects. I think they are well set, and that's just going to go expand. But if I look at things like rooftop 10 kilowatt hour project, something which can be put in a public health center in a small town, something that can go on to schools, that seems to have flunked. Can you comment on both these questions?
Sure, and I'll just kind of note the questions so I don't forget them. Yep. So the first is group captive. Are there other models the regulators are thinking about? And the second is about why is rooftop, especially smaller rooftop, not taking off the way other solar in other sizes of solar are. So excellent questions both. Regarding the first, I think there is no constraint in simply allowing people to do, if that's where you're going, sir, allowing people to go third party, which is like the customer does not need to invest a 26% of the equity, which is the group captive structure, which is a structure that was created under the Electricity Act 2003. in order to enable people to build their own plants. When they say own plants, they only had to invest 26% equity. Now, third party can be permitted, but really it's a sort of a difficult juggling act that the government has to engage in with respect to the health of discoms, as well as so health of discoms while enabling solar. If they were to make a third party too easy, or they were to not charge a fairly large amount of a very, very high charge that applies to what is called, you're familiar, cross subsidy surcharge or additional surcharge. These amount to nearly 3 rupees in some states, in other states 1.5 rupees. So very significant. And that is what is avoided by going into the under the group captive structure. If the government were to try to waive these, right, and then I think the discounts would suffer some more. Now, the question you could ask, and we have obviously a highly intelligent and highly intellectual set of people on this call, so they will look at it differently than say it might be looked at in the say government or business world. That essentially you're saying that I have built a bad engine, right, which is my entire coal production, discom, losses, etc., and I have to support that engine. I cannot suddenly go to the newest, nicest, cheapest technology, which also happens to be green. So not an ideal answer. I mean, obviously it's not my answer, but it's the, I'm saying that.
I think you have answered the question.
Sorry? Yeah.
You have answered the question.
So that's one. And then as far as the, so in short, whether it is group captive, open access, or even large rooftop, let me be rather forthright here with, with sort of this esteemed audience, that no, the government isn't doesn't make it too easy. That's, we can tell you that, because we have also dealt with every flavor of it. They don't make it too easy, and these are the very, very best customers, the very, very best customers who pay and who pay the highest rate. An approach could be, of course, let's make the power for our best customers cheapest, and then of course that would cause the industry to grow, etc., etc. But that's a socio-economic question, not a solar question.
Even in group captive,
yep,
we land up paying about 2.50 rupees if I can combine the wheeling charges and the demand charges. So it is not that as if that is not being paid. It's a different matter that we are pushing the discom to also do banking. Assume banking goes away.
Understood.
Once banking goes away, if you sort of say no banking, or no banking more than 15 minutes or 1 hour, then at least we are still paying 2 rupees to 2.50 rupees. If you combine demand charges and wheeling charges. So it is not that a small amount of money is being paid. That
understood.
Discom or the transmission utilities.
Yeah, understood. I can't say that I entirely followed your point about the connected low, as in the demand charges, in the sense that obviously solar being intermittent can't replace or reduce the demand capacity, but you're still paying a rupee and a half in losses, in wheeling charges, transmission losses, SLDC charges, etc. So that is correct.
Plus demand charges.
Yeah. So fine. So I think so we know where all of this is coming from, and that's the driver, that we are paying enough. At the same time, the concern is that's still not enough, because after all, the best customers, when they were all there, not using solar, the discoms were not doing so well, and there wasn't enough to cross subsidize other parts of society. Then when they start going to an alternative source, then things would only get worse. So there's a balancing act that the government does.
Come to the second question.
Yeah. So second question is about rooftop. So I think that's a easier that's an easier answer for me to give, or let's say some people like us would be more of experts in it. And that is about portfolio size and financing. So it has, first of all, smaller projects obviously have a larger cost. Second, our residential sector, unlike many of the other countries, our residential sector is subsidized. So when it costs about 16 rupees to deliver that power, we are charged only 8 rupees because the city grids are hardest to maintain, etc., etc. So point being that, we are already, that power is subsidized. So when you compare the cost of rooftop solar, in the first place, it doesn't save too much money. Secondly, if you do a lot of rooftop projects together of a smaller size, you'll still not get to a large portfolio. And when you're looking at infrastructure asset financiers, be they equity or debt, it's hard to get them out of bed for less than $100 million US dollars. So it's exactly the same leap of faith that people like us took about 7 years ago, where C&I belonged to exactly the same category. There was a
be honest.
Sorry?
Yeah. Any other question?
Yeah, sorry. So that's it. So that's basically the reason.
Can I ask a question,
please,
Ravi?
Yeah, go ahead.
So Anurag, this is Ashish Garg from IIT Kanpur. So given that there has been a massive surge in solar installations across the country, India being a very dust-prone country, and there is also a problem with recycling of these solar systems. How do you look at the longevity of these projects as a function of time, and how long do you think this kind of subsidized model will continue?
Yeah, and when you say subsidized, you mean subsidized in which form?
I mean, you're saying that right now there's a massive discount with respect to grid cost of power, as well as, so I mean, 3 rupees per kilowatt hour probably is right now the price in the market. That is probably not a sustainable price, right?
Right. Okay. So let me address that. So actually, the price is working out to that without any significant subsidies or significantly lower GST or anything else. It just so turns out that yes, when people are bidding those large government projects, the 2 rupees 75 paisa and 48 paisa that you come across, that's basically competitiveness and the desire to build that portfolio that I was referring to a minute ago, right? That you need the portfolio, otherwise you can't even stay in business. So you need that. Right. But before I entirely go to the question, your question, because it's linked a little bit linked to the previous one, I'll sort of continue on that one, which is that it is important that somebody takes that huge leap of faith, as people like us did 7 years ago on C&I, and said, if you build enough of these, there will be a portfolio. So similarly, if you build enough rooftop projects, there will be a portfolio which is sizable enough that your biggest component and driver of LCOE, and to this audience, I mean, you know this inside out, is the financing cost. It's not the cost of component. You can bring the cost of a component down with great difficulty and great scientific and technical innovations rather, that all of you are engaged in, by 5%. But if I were to lower the IRR by 1%, that will have a disproportionate impact on the LCOE. So that would keep a price like 3 or 4 or 4.5, maybe 5 rupees per unit sustainable for the small rooftop segment. For large projects, anything more than 10 megawatts, that number 3.5, 4 is already sustainable. But then I'll go back to your original question, and all of you are more of experts than people like us are, in the sense that what happens to all these modules 25 years from now. As you know, some of the companies earlier used to sort of have a plan, an insurance and recycling plan attached to the modules, wherein they would take them back. But eventually customers were not paying enough for it. So this was done at the end of module manufacturers to have a higher brand, if you will, right? Not much of that is being seen, Professor. So, but it's something that we should drive towards, because in 25 years, all of the silicon and some of this CAD/TEL would require, definitely to be recycled.
Yeah.
Yeah, we need to stop now. I think we have gone way past the time.
Thank you, Anurag.
I think we want to thank all the speakers, all the participants.
Thank you, Anurag, for that presentation. And firstly, I want to just say thank you to all our presenters for sharing with us your thoughts and insights. We've had a very detailed discussion on a wide range of topics, and we hope to sort of continue this tomorrow, starting 2 p.m. India time. And I hope many of you will join us back so that we can continue some of these discussions. We have a number of expert speakers lined up for tomorrow, and hope many of you will be able to join us again at the same time. You can use the same link that you used today for the call tomorrow as well. And we look forward to sort of having everyone there. And thank you again for all our presenters and our attendees for joining for this deep dive on sustainable energy, and hope to meet you all again tomorrow on the same Zoom link.
And please be on time, because we would like to start on time. 2 o'clock, not 2:30. 2 o'clock. Those who are in IIT Madras should come here.